Hello class, welcome to this video on the geometry midterm review. So we're going to go over everything from the beginning of the year up until this point, the mid portion of the year. And this is going to be stuff for cycle 2 assessment. So we're going to break this up into various benchmarks or various topics, and we're going to have problems related to those topics. So the first topic or standard here, or benchmark if you will, is to prove relationships and theorems about lines and angles. Solve mathematical and real-world problems involving postulates, relationships, and theorems of lines and angles. So the first example here is if angle 1 is congruent to angle 3, which conclusion can be made? All right, so first off, what we're going to look at here, the concept here that is they're testing you on is the idea of two parallel lines or two lines crossed by a transversal. So the transversal here is the line that crosses two or more lines. So this here is a transversal, and you need to know that when two lines are across a transversal, they form special angle pairs that you need to know the names of. Okay, so first special angle pair is alternate exterior angles. So for example, they're outside the two lines and they're opposite sides of the transversal. Those are known as alternate exterior. Alternate interior angles are angles that are inside the two parallel lines and they're on opposite sides of the transversal. Like so. Not only are they on opposite sides, but one is on the left, one is on the right, but there's one on the top, one on the bottom. So they're opposite in every sense of the word. All right. And then if they're on the same side of the transversal and inside the two lines, we call that same side interior or consecutive interior. All right. And then lastly, the last of the main ones that they test you on is corresponding angles. So corresponding angles are two angles that are, for example, they're on the same side of the transversal, but one of them here, let me get rid of that angle 6 there because I don't need that angle for this, but one of them is usually inside the two lines and the other one is outside the two lines. So one is usually inside, one is usually outside, and they're on the same side of the transversal. So 1 and 5 fit that profile. They're on the same side of the transversal, and one is inside, one is outside. That's one way to think about it. They're corresponding because, you know, if I can slide one, it usually would match up, right? They're on the same corresponding location. All right, so if these two lines here are parallel, then that means that the alternate exterior angles are congruent. That also means that the alternate interior angles are congruent. And that also means that the same side interior angles, these two add up to 180 degrees. And lastly, that would mean that the two corresponding angles, 1 and 5, are congruent. So in this case, if we look at this example, 1 and 3, they tell you that they're congruent. So if they're congruent, well, look at these two. If I just look at these two lines in transversal A, and I ignore B, let's just ignore B for a second, that forms the situation we see here. Well, these are corresponding. 1 and 3 are corresponding. So therefore, if they're corresponding and they're congruent, that means that these two lines must be parallel. So C must be parallel to D. All right. If they told you that 1 is congruent to 2, well then in that case that would tell you that we would have to ignore D, and then we would say that A is parallel to B, because in that case 1 and 2 would be corresponding and they corresponds to A and B being parallel. But in this case we're not looking at that, we're looking at 1 and 3. All right, so for example 2, given that lines C and D are parallel, so these are parallel, so we indicate that with an arrow on the two lines, determine the values of X, Y, and Z. All right, so if I just focus on these two parallel lines and this transversal, and I ignore everything else on the diagram, just ignore everything else, then I have the situation with the transverse line, right? So notice that these two angles are alternate exterior angles. They're outside of the two lines. So these are going to be congruent. As long as these two lines are parallel, alternate exterior angles are always congruent. X equals 109. That's by alternate exterior angles theorem. All right, and then to get Y, So if I just focus on y, well, look at this triangle right here. So the three angles in the triangle always add up to 180 degrees. So I can get y by taking the sum of the other two angles and subtracting it from 180. So that's known as the triangle angle sum theorem. So to get y, I have to simply do 180 minus, and then add those other two angles, 55 and 41, subtract that from 180. So I get 180 minus 55 plus 41 is 96. Subtract that from 180 to get 84 degrees. And this is known as the triangle angle sum theorem. All right, and then lastly, to get z, well, there's a couple of ways to get z. One of the ways to get z is to, if I look at this triangle and then I look at this line that is outside of that triangle, if I have any triangle and I have a line that is exterior to that triangle, where this is an exterior angle, I can always take the two angles that are farthest away from that angle inside the triangle and add them together. So in order to get angle 1, I would have to add angles 2 and 3. This is known as the exterior angle theorem, the triangle exterior angle theorem. So that's one way to do it. Another way to do it is the fact that if I just focus on this line and y and z, so if I focus on this part where y is 84, right? And then I'm trying to figure out what z is. Well, this is known as a linear pair. A linear pair is a line split into two, essentially. So a linear pair always adds up to 180 degrees. So z plus 84 is 180. So I can get z by doing that as well. That's known as a linear pairs theorem. So there's a couple ways that you could do this. So we'll go ahead and invoke the linear pairs theorem for this. But we'll go back and revisit the exterior angles theorem and later on in the review. So this is going to be 96 degrees, it appears. And this is the linear pair theorem. All right, so third example. Here, Jesse is trying to prove that the three angles in a triangle add up to 180. So Jesse is trying to prove the triangle angle sum theorem. And in doing so, he starts off with two steps in his proof. So he says that angle 2 is congruent to angle 4, and he says that angle 3 is congruent to angle 5. All right, so let's just focus on, for example, just for this instant, for 2 and 4. Well, notice that these two lines are parallel, right? Because it says so here. And if they're parallel, then if I just focus on this transversal, ignore this for a second, then I have two parallel lines and one transversal. Those angles there are inside, so they're interior, and they're on opposite sides of the transversal, so they're alternate. So they're alternate interior angles. So by the alternate interior angles theorem, they must be congruent. So, first off, just to review, alternate interior angles are congruent. So if I have two parallel lines and I look at 1 and 2, well, I know that angle 1 must be congruent to angle 2 as long as these are parallel. That's alternate interior. If I had angles 3 and 5, these are alternate exterior. These are also congruent. If I had if I had 6 and 2, right? Well, then angle 6 and angle 2 are not congruent. They're on the same side. They're consecutive interior, but they're not congruent to each other, but they add up to 180 degrees. So I would say that the measure of angle 2 plus the measure of angle 6 equals 180. And then lastly, if I had another angle here, angle 3 and angle, well, I don't need that actually. I don't need that angle. Angle 3 and angle 2 are congruent. These are corresponding. Corresponding angles are always congruent. Okay, so you got the rest of most of the angles are congruent. The only ones that are usually going to be supplementary are, out of the four mentioned, are the ones that are on the same side and inside the two lines. If you had two exterior angles, like 3 and 7, that are on the same side, they're also supplementary. Anyway, so that was just a quick aside, because this is a review, so I want to make sure I review different things. So in any case, this is going to be alternate interior angles theorem for both of them. Okay, so 2 and 4 and 3 and 5 are alternate interior angles, because if I ignore this, I can draw this line, and these are alternate interior. All right, so both of them are justification is alternate interior angles theorem. So if I look at example 4, again, if these are parallel, because we want them to be parallel here, this is the symbol for parallel, well then these two angles are alternate exterior angles, and like I said, mentioned earlier, those two must be congruent. So therefore these two angles are congruent, so we can set them equal. All right, so solving this, I'm going to subtract 4x on both sides. If I do so, I get 5x minus 12 equals 6. Next, I'm going to add 12 to both sides. That gives me 5x equals 18. And then finally, I'm going to divide by 5 on both sides. So that gives me 18 over 5. 18 divided by 5 is 3.6. So then remember, don't get too, trigger happy here and try to get the answer right away. The answer is not A, because we're trying to answer this question here. Find the measure of angle LMN. Well, the measure of angle LMN, this is LMN right here. So we're actually looking for this side here, or this angle. So we're going to plug this into this angle. So the measure of angle LMN is equal to, we have 4x plus 6, but x is 3.6. So if I do that, I get 20.4 degrees. All right. Let's take a look at the next topic here. Usually each topic is going to have 2 to 4 questions. Most of them will have 4 questions. Some of them have 3 or 2. All right, so prove triangle congruence or similarity. We're not going to prove similarity here because we're going to cover that in the next part, the next half of the next semester. We're going to cover it. This first semester we covered congruence. All right, so we're going to talk about that. So example 1. If MQ is congruent to PN, are the two triangles congruent? So we're looking at this triangle here, and then we're looking at this triangle here. All right, so they tell you that MQ is congruent to PN in the first statement there. They also tell you that these two angles are congruent. That angle and this angle are congruent because they put it on the diagram. So it looks like we got a side and we got an angle. Side and an angle. All right, so do we have another side? And the answer is yes. You see this side that they share? Those two triangles share a side in the middle. That side in the middle that they share, let me get rid of all this stuff now. They share this side in the middle, which means by reflexive property, the side is congruent to itself. So that side is called PM, right? And we know that PM is congruent to itself. In other words, the triangle with the side PM matches the triangle with side PM on the other triangle, right? And they must be congruent. So by reflexive property. I'm going to write the name of it so that you can remember, or just how what it's called. So therefore, this is congruent to itself. And therefore, we have another side. So we got side, angle, side. Side, angle, side, side, angle, side. So they must be congruent. The theorems that we use to prove congruence are side, 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 angle, side, angle, side, angle, 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 side, and HL, hypotenuse, leg. Okay, and there's some other ones, but those are the main ones. So side, side, side means you need to know all 3 sides that match up that are congruent. Side, angle, side is what we just did. We have a side, we have an angle in between, and then another side. ASA is an angle, a side in between, and another angle. We have angle, angle, side, which is 2 angles next to each other, and then a side afterwards. And then hypotenuse, leg is for right triangles, as if you have a hypotenuse and then a leg. This is hypotenuse, that's a leg, and it has to be for right triangles. All right, so that's a quick summary of what we did for those theorems. But in this answer, this one's SAS, so the answer is A. All right, so for example 2, we're going to go through the entirety of the proof and then answer the question at the end, just to get your practice with it. All right, so we're given that S is the midpoint, so we're going to put that in step 2, right? Step 2, we're just saying, oh, S is the midpoint, that's given. We could also have put that in step 1. It doesn't really matter, step 1 or step 2. Now, for step 1, we said that BSO is congruent to TSA, And that's because these two angles are congruent because they're vertical angles. Vertical angles are when you have two lines that cross and you're looking at the two non-adjacent angles, the two angles that are opposites of each other. Those two are always congruent. Just like these two are congruent as well. Those are also vertical angles. All right, so vertical angles theorem, that takes care of statement 1. So those two angles must be congruent. And then because we know that S is the midpoint, that means this is in the middle. And if this is in the middle, that means that this is congruent to that. That's by definition of midpoint. And then so it looks like we got an angle, we got a side so far. And then we know that these two are parallel because it says that right here. And therefore, what we can say is, okay, well, if I draw these two parallel lines, let me just erase everything else for a second just to eliminate confusion. So let's say we have those two parallel lines, and then this is the, if I look at the transversal, let's look at this right here, this transversal. Well, then I know that this must be congruent to this because those are alternate interior angles, right? They're inside the two lines and they're on opposite sides of the transversal. So that's alternate interior angles. So that's how we know that those are equal or those are congruent. All right, so far we have those are congruent. We have that these are congruent because of vertical, and we have that these two sides are congruent. So it looks like we have angle, side, angle, right? Angle, side, angle. So therefore, these two triangles must be congruent by angle, side, angle. Congruence theorem. Okay. All right. So for example 3, given the triangles below, determine whether they are congruent using SSS criteria. Now SSS means that if you look at two triangles, that one side is congruent to the other, this side is congruent to that, the other side is congruent to the other side. So we got side, side, side. So we have to show that all the sides are congruent. Or if we show that one of the sides that match up are not congruent, then we can say it's not congruent using SSS. Okay? So what we're going to say is that, well, we know that AB must match up with DE, and if it does not, then it's not congruent by SSS. That's all. So if we can show one of them does not work, then, you know, if we can show that there's at least one pair that doesn't work, that doesn't have the same length, then it's not congruent by SSS. All right, so let's find the length of AB. So let's focus on AB first. So to find the length of AB, you can count up and over. So it goes 1, 2, 3, 4. So it goes up 4, and it goes over 1, 2, 3, 4, 5, 6 spaces. And then since we got 4 and 6, right? We want to figure out what this length is. So we can figure out that length using the distance formula. And so the distance formula, in this case, this is A, or this is B, and this is A. So to get AB, you know, AB is equal to the square root. You use those two sides, 4 squared plus 6 squared. This is using the distance formula where you're just counting instead of subtracting the coordinates, you're just counting it. So 4 squared plus 6 squared, and that gives you the length. So 4 squared is 16, 6 times 6 is 36, and so this is going to be square root of 52. All right, so we got AB. Notice that we don't have to actually calculate this. We just want to see that the numbers are the same. Now let's go ahead and do DE. So it looks like it goes 1, 2, 3. It looks like it's going 3 over, and it's going 1, 2, 3, 4, 5 up. So it looks like you're going 3 and 5. So if I want to figure out what this length is, that's length DE. I need to do the square root of 5 squared plus 3 squared. So 5 times 5 is 25. 3 times 3 is 9. So this is square root of 34. Notice they're not the same number. 52 and 34, completely separate numbers. So these two are not congruent. And therefore, these two triangles are not congruent by SSS. If you do the other pairs of sides, they're also not going to be congruent. So the triangles are not congruent by SSS. All right, so for the fourth and last example of this topic, if we look at, we're going to try to prove this here. LE, we're going to say that LE bisects angle L. And this is angle L. We're not trying to prove that. They give us that. They told us that. So because that's given, well, what does it mean to bisect? If this EL bisects this angle L, well, that means that this angle has to be the same on either side, okay? And so we can see that GLE is congruent to ELU, or ULE, same thing. And this is by definition. That's what it means to bisect, right? So it's a definition of an angle bisector. All right, and now LE is congruent to LE. So if I look at this, well, this is obviously congruent to itself, right? Because it's the same thing. So LE is congruent to LE. So LE is congruent to itself. That's what they're saying. So when we have something is congruent to itself, LE is congruent to LE, A is equal to A, whatever, that's called reflexive property. So this is a reflexive property. LE is perpendicular to GU. Perpendicular means, that's this symbol right here, perpendicular means it crosses at a right angle. So this is a right angle. They're saying LE is perpendicular to GU. So they cross at a right angle, and that's what that's saying. All right, and if that's a right angle, this is a right angle. And if these are both right angles, then they must be 90 degrees. And if they're both 90 degrees, then they must be equal. That's what they're saying here. They must be congruent. So then, so angle GEL and UEL are right angles by definition of perpendicular, because that's what it means to be perpendicular. And then because they're both right angles, then they must be equal because all right angles are congruent. That takes care of this one. All right angles are congruent. And therefore, now if I look at this angles, I got angle, side, angle, angle, side, angle, right? The right angle, the side here in between, this acute angle. And so we got ASA. So the two triangles must be congruent by ASA. And that's the end of the proof. All right, so let's look at the third topic, or third benchmark. Prove relationships and theorems about triangles. Solve real-world problems involving postulates, relationships, and theorems of triangles. So this one's gonna talk. A lot of these are gonna involve like angles in a triangle add up to 180 degrees, that kind of stuff. This concept is testing you on the fact that this is an isosceles triangle. An isosceles triangle is a triangle with two sides are congruent. Equilateral is when all three sides are congruent. So here, this is isosceles. So by the isosceles triangle theorem, because we have two sides are congruent, that means two angles must be congruent. But which two angles are they? Well, the two angles that are congruent are the angles that are opposite of the congruent sides. So 62 is opposite of this congruent side, and angle A is opposite of this congruent side. And therefore, angle A and angle C must be congruent. And this is called the isosceles triangle theorem. Okay, so then we know now that using this opposite technique, we can get the angles that are the same. And so this is 62 degrees. These must be congruent. And to get angle B, we know that the three angles inside must add up to 180 degrees, and that's known as the triangle angle sum theorem. So to get angle B, I have to do 180 minus, and then I have to add the two angles 62. So that's 124, and then I get 56 degrees for angle B. This is known as the triangle angle sum theorem. All right, so that takes care of this. All right, so example 2, what is the value of x and y? Now, looking at this triangle, we know that the angles must add up to 180 degrees by the triangle angle sum theorem. So I can get y. So y equals 180 minus 46 plus 51. That's 180 minus 97. So if I subtract that, let's see, I get 83 degrees. All right, so that's the triangle angle sum theorem. And now we also know that these two angles, y and this angle, must be congruent because they're vertical. Vertical angles, recall, are where you have two intersecting lines and you're looking at the angles on opposite ends, on opposite sides that are non-adjacent. So if y is 83, then this must be 83 by vertical angles theorem. And then next, we know that these three angles in this triangle must add up to 180 by the triangle angle sum theorem. So we got 180 minus, add those two other angles, we have 83 plus 38, that's 121, and subtract those to get 59 degrees. All right, so that takes care of example 3. Let's look at example 3. So remember earlier we mentioned that if I have a triangle and I use an exterior angle, I draw out an exterior angle, an angle that is on the outside of the triangle, in this case angle 1, I can get that angle by adding the two remote interior angles. These are the angles that are the farthest away from angle 1, and that would be angles 2 and 3. So, in other words, to get the measure of angle 1, I have to add the measure of angle 2 plus the measure of angle 3. These are the two ones that are the farthest away. These are known as the remote interior angles. All right, and this theorem is known as the exterior angles theorem. It may also be known as the triangle exterior angles theorem. Okay. All right, so in that case, we need in order to find the exterior angle, we would need to add the two remote interior angles. All right, so in that case, 5x plus 62, that's the exterior angle. You can get that by adding the two inside remote interior angles, so 37 and 3x plus 47. And then we can, of course, solve. So if I solve this, combining like terms here, I get 37 plus 47 is 84. I'm going to move the 3x over and subtract it. So this is going to be 2x plus 62 is 84. Next, I'm going to subtract 62 on both sides. And if I do that, I get 2x is equal to 84 minus 62 is 22. Divide by 2 on both sides to get x equals 11. And so now we know x is 11, which they tell you here anyways, but it's good to practice. If we plug in 11, we're looking for the measure of each angle. So we're going to plug in 11 into these guys. So we get 3 times 11 plus 47. And then we have 5 times 11 plus 62. Well, 5 times 11 plus 62, that's 55 plus 62. And that's 117. So that takes care of, so that it looks like the answer is going to be B. If I do 3 times 11 plus 47, that's going to give me 80. So the answer is B. All right, so let's go ahead and take a look at the last example in that topic. Find the measure of angle DAC. So we're looking for this angle right here. We do not know what that angle is equal to. So DAC, the measure of that. But we know that to find the measure of angle DAC, we know that this is a 90-degree angle right here. And we know that this right here is an isosceles triangle because these two, those two sides are the same. And we know that in an isosceles triangle, by the isosceles triangle theorem, the two opposite angles, the angles that are opposite of the congruent sides, must be congruent themselves. So these two opposite angles, 1 and 2, must be congruent. And therefore, if this is 67, then this here must be 67. All right, and then we can figure out what this third angle is, right? So we're going to call that x. So we're going to say that the measure of angle DAC is equal to x. And so if we do that, we get x plus 90 plus 67. If I add these three angles, 1, 2, 3 must add up to 180. So in order to get that, I do 180 minus 90 plus 67. So 180 minus 157 is 23 degrees. All right, so that takes care of that. So let's take a look at the next topic, benchmark. Given a pre-image and an image, describe the transformation and represent the transformation algebraically using coordinates. All right, so we're going to do transformations in this one. So we're going to, it says identify the transformation and write the coordinate rule for the transformation. So, so for this, there's one transformation going on and we just want to identify what that transformation is. So first off, we know that this is the pre-image, this is the image, right? So we know that this is the pre-image because this is A, and this is the image because this is A prime. If you see that little symbol there. All right, so let's see. We know that A goes to A prime. A is 1, 2. If I look at the image here, then the coordinates of A prime are 2. This coordinate right here is 2, -1. So A prime is 2, -1. So you can see that the coordinates switched, and not only did they switch, they there's a negative on the second coordinate once you switch them. So in other words, the coordinate rule here is x, y. You switch the coordinates. So if this were 1, 2, this will now turn into 2, 1. And then you put a negative here because we want this to be negative. So this is the coordinate rule right here. So the coordinate rule, x, y maps to y, -x. That seems to be what's happening here. And this, if you notice, this is a rotation. This is a rotation. This is actually rotated this way, right? So it's rotated 90 degrees. We can tell it's rotated 90 degrees, and it's rotated 90 degrees clockwise. So this is a 90 degrees. So rotation 90 degrees clockwise about the origin. There are a couple reasons I know this. A couple reasons. So the first reason is that if this is the origin and this is a line from the origin to A, well then if I rotate that line about the origin, that lands me at A prime. Well, notice that that's a right angle right there. So that's the reason number one. Reason number two is that I know that this is the rule for rotations that are 90 degrees. So let's go over all those rules real quick. So you need to know these rules for the EOC and for the midterm as well. So make sure that you commit these to memory. So if you want to do a 90-degree rotation counterclockwise, the rule is you take the coordinate and you switch the coordinates, and then this first coordinate is negative. Once you switch them, the new first coordinate is negative. For 180 degrees, you take the coordinate and you negate both the x and the y coordinates. So x, y goes to -x, -y. And then finally, if I do 270 counterclockwise, then I take the coordinate, I switch the coordinates, and I negate the second one. So this is going to be -x. All right, those are the coordinate transformation rules. Now keep in mind that in this example, we were doing a 90-degree clockwise. These rules are for counterclockwise. So therefore, 270 degrees clockwise is the same as 90, or 270 counterclockwise is the same as 90 clockwise. And 90 counter is the same thing as 270 regular clockwise, okay? So keep that in mind depending on whether they're asking for clockwise or counter. But these are the rules, so dedicate these to memory so that you are okay with rotations about the origin. Okay, so example 2, write the coordinate rule for the transformation below. All right, so this is clearly a translation. It's being moved. So we just have to figure out how much did it move from A to A prime. Remember, we're going from A to A prime. So we're going from the image to the pre-image to the image. So we're actually starting at A and then B to B prime. All right, so 1, 2, 3. So we're going 3 up. 3 up is positive. 1, 2, 3, 4, 5. 5 to the left, that's -5. So the transformation rule is you take the coordinate. Well, let's write the coordinate rule over here. The coordinate, and you move it up 3 and left 5. So left 5. Left 5 means you take away from x, right? So you take the x coordinate and you move to the left. That's in this direction. So that's -5. And then you're going to move up, right? So up is plus. So you're going to add that to the y. So left 5, up 3. All right, and that's your coordinate rule. Move everything to the left 5, move everything up 3. All right, so example 3, which transformation maps the solid figure onto the dashed figure? All right, so it's clearly not a translation because it's not moved. If I move it, then it's gonna maintain the same position, right? So therefore, that can't be or just a translation. It can't just be a reflection over the x-axis either, because if I reflect it over the x-axis, I'll get something that looks like, it'll look kind of like that, right? It's not, this is not perfect, of course, but something like that. I'll get something that looks more like that. All right, so it can't be that. It can't be a reflection over the y-axis, because if I did that, it will get me something like this. So it'll get me something like that, right? So we can't do that. But it could be a rotation. So if I rotate this 100 from here to here, if I take this and I rotate it 180 degrees, that will get me to that position about the origin. So the answer is A. All right, which transformation rule can be used to transform the pre-image to the image? All right, so we're going from this to that. It looks like it's a reflection about the y-axis, about here. Okay, so if I flip it, I get the one on the left. So if it's a reflection about the y-axis, what's changing? Well, A is going to A prime. So if A is xy, well then what's A prime going to be? Well, the only coordinate that's going to change is x, right? So if I flip xy to the other side, well, that's going to give me negative xy, right? Because x is going to be on the opposite side. It's negative. The y is going to stay the same. That's if I reflect it about the y-axis. So the answer is xy goes to negative x comma y. In other words, if I have 1 comma 2 as my a, then if I reflect it over the x-axis or the y-axis, I get negative 1, 2, for example. All right, so let's look at the next topic / benchmark. Identify transformations that do or do not preserve distance. All right, so the vertices of triangle JKL have coordinates J, so they give you the coordinates JK and L. Under which transformation is the image not congruent? So not congruent. So remember, if we do, so there are transformations known as rigid transformations. This is what they're testing you on. They're testing you on this concept of rigid transformations. Rigid transformations are transformations that you do to something in order to, you transform it, but you do not, you preserve the shape of, you preserve the size and the angles of that particular shape or object. So for example, if I do a translation, that is not going to change the size of the object. It's simply going to move the object. It's not going to change the size. It's not going to change the angles. So if I start off with a right triangle and I move it, it's going to remain a right triangle, and it's going to stay the same angle, same size, everything. If I do a rotation, so if I take this triangle and I rotate it, right? Well, in that case, if I do a rotation, then it may end up looking like for example, it could look like this, right? So it could look like that, where it got rotated. But notice that it's still a right triangle and the sides are still the same length, right? So for example, this side still remains the same length as, for example, this side. This remains the same length as, for example, that side. Just giving an example here. And this side remains the same length as that. So that's known as a rigid transformation. And then lastly, if I do a reflection, that is also not going to change anything. So if I reflect this about the x-axis, it's going to be like this. It's going to look like this, but this is still going to be congruent, this is still going to be congruent, this is still going to be congruent. The sides are not going to change. So those are the rigid transformations. Anything that is not one of those, or a combination of these, is going to be not congruent when you transform it. So translation makes it congruent. So this cannot be the answer because we want it to be not congruent. A rotation is not the answer because we want it to be not congruent, and a rotation makes it congruent. A reflection also makes it congruent, so we can't say C. Dilation. A dilation is when you stretch it. So if you're doing by stretching a factor of 2, it goes from this size to twice the size, right? That makes it bigger. That makes it not congruent. So the answer is D. All right, as shown in the diagram below, when the right triangle DAB is reflected over the x-axis, its image is triangle DCB. So we're doing a reflection. That's a rigid transformation. Therefore, it's going to remain congruent. So distance is preserved on the reflection. That is true. The size is not going to change. Orientation is preserved on the reflection. That is not true because this here got reflected here and it changed position. So that is not true. Points on the line remain invariant. That is not true. Invariant means it doesn't change. It does change. The coordinates of A change to the coordinates of C. Although D and B remain the same, A and C do not, right? A changed. Right angles remain congruent under reflection. That is true. If I have a right angle, then this is going to be congruent to that. Okay, so we have two choices that are congruent. So 1 and 4 are congruent. All right, so the vertices of triangle JKL have the following coordinates. On which transformation is not congruent? I think we did this one already, right? The answer was dilation. So this one is actually a repeat question. All right, so looking at the third or looking at the next benchmark topic, identify a sequence of transformations that will map a given figure onto itself or onto another congruent or similar figure. If I look at this question here, it says triangles ABC and DFG are shown. Which pair of transformations will carry ABC onto DFG? So a sequence of transformations is when you have multiple transformations going on. So one after the other. So in this case, what two transformations will make this work? We want to go from this to that. So notice that A maps to D. And we notice that from here, B maps to F, right? And from here, C maps to G. So we know which one goes to what. So let's go ahead and do B. We know that B should map to F, right? So let me just focus on B. We know that the coordinates of B are 4, 5. From this here, we got 4 and 5. We know it should map to F, which is F is here. It's -5 and -4. Well, then if we do that, okay, so then we're going to go through these transformations one by one and see if that takes us from B to F. So let's do A. We are rotating 90 degrees clockwise. So B is 4, 5. Let's go ahead and rotate 90 degrees clockwise and see if that gives us the answer. Remember the rule for 90 degrees clockwise is XY maps to Y -X. So that's the rule. You got to remember those rules. We went over that in the previous example, one of the previous examples. So 4, 5 maps to, in this case, if you switch the coordinates and then the second one is negative, that's 5, -4. Okay, that takes care of the first transformation, followed by reflecting it over the y-axis. If I reflect something over the y-axis, that's going to change the x coordinate, right? So it's going to go from +x to -x and vice versa, right? So it's going to basically put a negative in front of the first coordinate. So the x coordinate here is now 5. So it's going to be -5, -4. Now, is that the coordinate that we want? Yes, that is the coordinate that we want. F is -5, -4. So check. That seems to be the transformation. This should also work for from going to A to D and going from C to G. If that does not work for those transformations, then this is not correct. But I will not verify that. You can verify that as an exercise to verify that A goes to D and C goes to G using these transformations. All right, so example 2, determine the sequence of transformations that will map the pre-image to the image below. All right, so first off, notice a couple of things. A is here on this side, but A prime, this is A prime. A prime is on the left side, but it's on the right side of the figure, whereas it's on the left. It starts out on the left side of the pentagon, the pentagon. But then it ends up flipping over so that it ends up on the right side of the pentagon, right? So this has actually been flipped. So this is a reflection. So we know it's been reflected. So first, what we're going to do is we're going to move the figure down and then try to reflect it, okay? So, and then we have to not only move it down, but we also have to move it over. Okay, so we know we want to reflect this around the y-axis, right? Because if I flip it, it'll get me something like that. So, so first off, what I'm going to do, and it actually doesn't matter. You can flip it and then move it. So actually, let's do that. So let's go ahead and flip it. So if I flip it, I get 1, 2, 3, 4. 1, 2, 3, 4. So then P is over here. Or actually, I don't want to flip that. I want to flip this guy. This is the pre-image. We want to flip that guy. So if I flip this guy, this is 1, 2, 3, 4, 5. So this is 5 units away. So when you reflect it, it should be 5 units on the other side. 1, 2, and actually, let me see if I can change color here. Okay, if it lets me, see if I can change the color here. Yeah, let's do this color. Okay, so for here, we got 1, 2, 3, 4, 5. 5 spaces. So P is actually going to go here. And then A, again, 5 spaces over. Oh, I'm sorry, not 5 spaces. I'm sorry. It's only A is about 2 spaces there, so it's going to be about 2 spaces here. So that's going to be about where A is, right? And you get the idea. P, A, and then it's going to look something like that, okay? We're not too concerned with all the other coordinates because we're really just concerned with a couple of coordinates. So we know that we can move P5 to the other side, and then we want to get P to map to here. So we're going to do this 1, 2, 3. So you got to go up 3, and then we're going to go over 1. So if we reflect it, and then we go up 3 over 1, that'll take us to where we need to go. Okay. Same thing here. This is where T will end up, and then if I go up 3, 1, 2, 3, and over 1, that'll take us to where we need to go. Okay. So hopefully you get the idea. All right. So we're gonna do a reflection. So we're gonna go x, y. Maps to a reflection over the y-axis means the x coordinate changes, right? So it's going to go, so this is a reflection across the reflection across the x-axis, or y-axis, sorry. And then it's followed by a transformation or translation. So we're going to take this and we're going to translate it. We're going to move it up 3 and over 1. So we're going to move it to the right 1 and then up 3. So right 1 is +1. Up 3 is +3 to the y. Okay, so to the right 1, up 3. Okay, so this is the translation. All right, so and that takes care of the sequence of transformations. All right, so you got to know what's going on and you got to be able to translate it into coordinates. All right, so the next example, a line has an equation given by y equals 3x plus 1. Suppose it is rotated 90 degrees clockwise and is translated an unknown amount. Which could be the equation of the line? Select all that apply. So what it's saying is that if you have an equation, you have 3x plus 1, you know, that's like an equation like this. That's a line, right? 3x plus 1. Where 3 is the slope, right? Remember that this is the slope. Y equals mx plus b. So we know that this is the slope. So the slope is 3 over 1. We usually write the slope as a fraction, put this over an invisible one because the slope is rise over run. So we know that this is the slope, and then it says you'd rotate it 90 degrees clockwise. And so if I rotate it 90 degrees clockwise, well then it doesn't matter where I rotate it. If they don't mention where, we're assuming rotate it about the origin. But it doesn't really matter because we're taking this and if we rotate it 90, it's going to look something like this, right? It's going to cross at a 90-degree angle. If I rotate it 90 degrees, it's going to cross the original line at a 90-degree angle, and which means that the two lines are perpendicular. So this is saying that the two lines are perpendicular lines. And if the lines are perpendicular, then we can find the equation of the line, or we can at least find the slope, right? We can at least find the slope. So two lines that are perpendicular always have slopes that are reciprocals, negative reciprocals of each other. So if I know that the original slope is 3/1, I can get the perpendicular slope of the perpendicular line by doing the reciprocal, switching or flipping the fraction, and then changing the sign. This is known as the opposite reciprocal or the negative reciprocal. So if this is positive 3/1, it's going to change into negative 1/3. So we need a line with a slope of negative 1/3. Well, that takes care of b, because we know that the slope is negative 1/3, because it's right there, y equals mx plus b. There are other possible answers though, all right? So we know b is an answer. We need to see if a is an answer. So what we're going to do is we're going to solve for y to see if we get a slope of negative 1/3. So let's solve for y. In order to solve for y, we need to subtract 2x, move the x to the other side. So this is negative 2x plus 5, divide by 6. If we divide by 6, we got to divide everything by 6. So y equals, notice that this becomes negative 1/3. So we do have a slope of negative 1/3. So a is a potential answer as well. So let's go ahead and check C. I'm going to erase this so that I can check C. Okay, so if I do 2y minus 6y equals 30, let's solve for y there. Or oh, this is a typo. This should say x right there, not y. 2y minus 6x. Okay, my bad. 2y minus 6x. So no, sorry, 2x minus 6y. This should be 2x minus 6y. Yeah, sorry about that. 2x minus 6y. So if I solve it, then subtract 2x on both sides. That's negative 6y equals negative 2x plus 30. But if I divide by negative 6, then this turns into positive 1/3. And 30 divided by negative 6 is negative 5. But that doesn't really matter. What matters is the 1/3. 1/3 is not a perpendicular slope. It has to be negative 1/3. So this can't be it. So it's not C. And then we're going to check one last equation. We're going to check D. Again, I know I'm going through these quickly, but this is just algebra, so I'm not going to spend too much on the algebra. We're going to focus more on the geometry concept here. All right, so y minus 3x equals 9. Let's go ahead and solve for y. Just move the 3x over. I'm going to add 3x to both sides. That becomes 3x plus 9. So the slope is 3. So this is not perpendicular. So the answers are A and B. Okay, so this is involving the geometry transformation, but it's involving the concepts of algebra and perpendicular lines. Okay, so looking at the next topic, benchmark, we have given a geometric figure and a sequence of transformations, draw the transformed figure on a coordinate plane. So again, more with transformations, but this time we're going to draw the transformed figure. So we're going to not only transform it, but draw it. And we're doing this with a sequence of transformations, so we're doing it with back-to-back transformations. Okay, now this one we're not, we could draw it. They want the coordinates, but we could also draw it. All right, the triangle is transformed by the following rules. So we got a sequence of transformations. We got transformation number 1, transformation number 2. Now transformation number 1 is a translation, right? And the translation vector is 2, negative 3. The translation vector, I didn't mention that earlier, but we did mention it in the class, right? A translation vector is it's telling you what direction it's going in. So it's going to the right 2 and it's going down 3. That's all it's saying. So basically it's saying exactly what this is saying, but it's just saying it in a different format. Okay, so it's moving to the right 2 and down 3. And then the next transformation is it's putting negatives on both coordinates. So this is actually a rotation, 180-degree rotation. So rotation 180 degrees about the origin. That's what the transformations refer to. You don't need to know what they do because all you need to know is how to use the coordinate rule, but you don't need to name it. Not for this problem. Okay, so let's take f. The coordinates of f are -4 and 2. So if I transform it, that becomes f prime. And actually, we're going to transform it twice. I forgot. So let's just say, let's just write down what the coordinate is in between. So let's do the first transformation. The first transformation is a translation. So we're going to add 2 to the x coordinate. Let me erase all this because I don't need this anymore. We're going to add 2 to the x coordinate and then subtract 3 from the y coordinate. So -4 plus 2 is -2. The 2 minus 3 is -1. So that takes care of the first transformation. Next, the second transformation, put negatives in front of x and y. Well, they already have negatives, right? So this turns into a double negative. Same thing for the 1, turns into a double negative, but a double negative turns into a positive. So this is actually +2, +1. And this is going to be f prime. So f prime is 2, 1. Sometimes we might refer to this as f prime and this as f double prime. In this example, they're referring to the final product as f prime. Okay? So we're going to do both transformations. All right, so let's do g. So g is 4, 6. And using the first transformation, we are adding 2 to the x coordinate, subtracting 3 from the y coordinate, again using this rule. 4 plus 2 is 6. 6 minus 3 is 3. Then we're going to transform the 6, 3 using the second rule, putting negatives on the x and the y coordinate. That turns it into -6, -3. All right, that's g prime. And then finally, let's do h prime. So h, the coordinates of h are 6, 2. So that's by the first rule, we are going to add 2 to the x coordinate, subtract 3 from the y, turns into 8, -1. Oh, I'm sorry, I'm not sure why I put -4 here. I should have put +4, 2. So that's I apologize for that. That's going to change the coordinates for f prime. I don't know what I was thinking when I did that. But yeah, 4 plus 2 is 6, not -2. And then if I put a negative in front of 6, that's going to make it into -6, sorry. So, but then the negative one will still turn into +1, but the 6 will turn into -6. Or, yeah. So it's going to be -6, 1. So apologize for that. Glad I caught that real quick. And then for h, we got 6 plus 2 is 8, and then 2 minus 3 is -1. And then if I do the second transformation, I'm going to put negatives in front of both of these. Well, that's going to make it into -8. That's going to turn this into a double negative, which is positive. So it's going to be -8, 1. And then we can, of course, graph this, but I'm not going to graph it. But you can graph it and see that it's the transformed triangle. All right. So let's look at a second example. It says figure 1 is reflected about the x-axis, and then... So we got a reflection about the x-axis, number 1, and then translated 4 units left. So that's 2 transformations back to back. That's a sequence of transformations. Which figure results? So we're taking figure 1 and it's mapping onto which one? All right, so the best way to do it is to first just pick one of the points and transform it twice and see which one, where it ends up. So let's pick this point right here, right? That point is, let's call that point A. In that case, the A is 2, negative. It looks like, if I look at it, let me erase this point for a second. Looks like it's 2, -2. All right, so if I reflect it about the x-axis, then it's going to reflect to the opposite side here, right? So basically, if you reflect about the x-axis, the y coordinate changes. So the y is going to be opposite. So this is going to turn into 2, double -2, which is +2. All right, so this is 2, 2. Then if I do the second transformation, that is translating 4 units to the left. Left means we're going 1, 2, 3, 4, right? That takes care of that. So 4 left means subtract 4. So 2 minus 4 is negative 2. So it takes us at negative 2, 2. So we're going to end up here. Well, the only one that works for is figure A. So the answer is A. That ends up being here, which is at negative 2, 2, which is what we said. All right, example 3 is triangle LMN congruent to triangle PQR. Justify your answer using rigid transformations. All right, so it says, all right, so if I look at this, let's take a look at the triangles. We know that LM has to go to PQ, right? So let's check the length. The length of LM is 2. So this is 2, and this is also 2. So these are congruent. So far, so good. For QR, this is 1 and 1, 2, 3, 4. And QR has to map to MN. So that's 1, 1, 2, 3, 4. That looks good. So these are congruent as well. And then lastly, PR has to map to LN, right? So if I look at this, this is 1, 2, 3, 4, 1, 2, 3. So 3 and then 4. That has to map to this 1, 2, 3, 4, 1, 2, 3. So they have the same numbers 4, 3, 4, 3. Therefore, they must be congruent. So these two triangles are congruent by SSS. They don't want that though. They want to do it with transformations. So what we're going to do is see what happens. So it can't be A because we know that they're congruent. It has to be A, B, C, or D. If I look at B, can I rotate it to 70 and then reflect it? Let's see if that's true. Okay, so we're gonna do a 270 degree counterclockwise rotation. So again, if you recall the rule for 270 degrees counterclockwise is the XY maps to y negative x. Okay, so if I use that transformation rule, we know that L must map to P. So, and we know that the coordinates of L are 1 and then 1, 2, 3, 4. We got 1, 4. So if I use that transformation rule, well then that's going to turn it into 4, negative 1. And then I'm going to do a reflection in the y-axis, which means that when I do a reflection in the y-axis, it's going to change the x-coordinate. So it's going to be negative 4, negative 1. And then we're going to verify that that actually maps to P. So we got negative 4. So P is actually negative 4, negative 1. So that actually works out. So this should be the solution here. We're going to check it with one more point just to be on the safe side. Let's do it for M. M is 3, 4. So M is 3, 4. If I use the rule for rotation, that turns into 4, negative 3. And then if I transform, reflect it about the y-axis, or the x-coordinate changes. So negative 4, negative 3. And then if I compare that, negative 4, negative 3, that gives me Q. So this works. So the answer is B. All right, so looking at example 4, the coordinates of rectangle ABCD are given. Find the coordinates of the image A prime, B prime, C prime, D prime under a 270 degree clockwise rotation followed by a reflection about y equals negative x. Okay, so we're going to take each of these coordinates. So let's take A, negative 3, 1. We want to do first a 270 degrees clockwise rotation. This was clockwise, not counter. So that means if 270 degrees clockwise is the same thing as 90 degrees counter. And we showed you the rule for 90 degrees counter, which is xy maps to negative yx. Okay, and if you want a way to memorize this, the way that I remember this is that if I start here, xy, if I rotate this 90 degrees counterclockwise, that takes me here, and this is 90 degrees counter. And I know that every time I do this is counterclockwise, CCW. Here, let me write this clearer. Every time I do a 90 degree rotation, it's going to switch the coordinates. So we got y, x, And we know that the first coordinate must be negative. So that gives me the rule that I see here, right? And then if I do another 90, I end up in quadrant 3 here. And we know that the coordinate has to be both negative here. Every time I do a 90, I have to switch the coordinates. Well, if I switch the coordinates here, that'll give me x, y, right? So this is another 90, and then this is a total 180. So let me write this as 180 counterclockwise. So then the coordinate turns into x, y, but both coordinates must be negative because you're in quadrant 3. And then if I do another 90, that's at 270 counterclockwise or 90 clockwise. And I switch the coordinates again, that gives me yx. And we know that the second coordinate must be negative because we're in quadrant 4. And that's a way to kind of remember the rotation rules. So maybe that helps. So if I were to do this for A, then it would be, I would have to switch the coordinates and then put a negative on the first coordinate, which is now -1, which is now 1. So it turns into -1. So that's transformation number 1. And then transformation number 2 will give me A prime. This is a reflection about y equals -x. If I'm doing a reflection about y equals -x, well then the rule is that xy, because it's y equals -x, that means that if y is equal to -x, that means x is equal to -y. So in other words, I can switch these. X is y and y is x, but they're negatives, right? Because y is -x and x is -y. So you just switch the coordinates and then both of them are negative. So in that case, we are going to switch them again and then put negatives. But if I do that, this turns into a double negative, right? And so this turns into +3 and +1. So it's 3, 1. All right. Now I'm going to show you another little cool trick here to kind of shortcut it. We know that if I take xy and I do this transformation number 1, it gives me -yx. If I do the other transformation, the y equals -x transformation, well, that's going to switch it back, right? And if I switch it back, it's going to turn into x -y. But then I have to put the negatives, right? So then I get the negative here and then a double negative for y. And this turns this into positive. And so the new rule is I can just go from here to here. And all I have to do, folks, is change the sign of the first one to its opposite, to the first coordinate. So A is -3, 1. Well, that's going to turn into +3, 1. Really simple, right? If I do this for B, well, B is 2, 1. If I transform it and go straight to the final answer, that's going to give me -2, 1. That's it. The y coordinate stays the same, and the x coordinate just has the extra negative. So I can really go straight to the answer. C is 2, -1. Well, if I do both transformations at the same time, one after the other, it's going to be -2, -1. And then finally, if I do D, which is -3, -2, I just put a negative in front of 3, which turns it into a double negative, which is a positive. It's going to be +3, -2. And that is your answer. And then, of course, you can graph it and get the transformed rectangle, but we won't graph it here. All right, so let's look at the next topic / benchmark. Apply rigid transformations to map one figure onto another to justify that the two figures are congruent. So you're going to apply the transformation just to see that they map onto each other. Okay, so which composition of transformations maps triangle ABC to triangle DEF? I believe we have done a problem like this already, if I'm not mistaken. Yes, we did. We found out that B mapped onto F, right? So B maps onto E rather, sorry, E. And C maps onto F. And I believe we said that it was A, but let's double check that just in case, because I can't remember. So 90 degrees counterclockwise, that rule is this. So y -x or negative yx, sorry, negative yx. And then if I follow that up with this translation, right, x plus 4, y minus 3, well, now I'm gonna basically add 4 to this coordinate and subtract 3 from this coordinate. In that case, it's going to be negative y plus 4 and then x minus 3. Because remember, the x is now the y in this example. All right. So if I do that, so basically it just means switch the coordinate, add, put a negative in front of the first one, add 4, take away 3. So if I do that for b, b is 3 comma 4. So when I switch it, it becomes 4, 3, but then put a negative here. And then you're going to add 4 and then take away 3. But that turns that into 0, 0. Straight to the origin, which that is not what we want because we want b to become e. And e is not at the origin, guys, so it can't be a. So good thing we checked this. So let's go ahead and check this for part b. So for part b, this time we are going to do the we're going to do x minus 4, y minus 3, so move it left 4, down 3, and then follow that up with a rotation. So if I rotate that 90 degrees counterclockwise, that means I need to switch the coordinates and then put a negative on the first one. Okay, if this looks confusing, don't worry about it. We're going to do it with the coordinates, with the actual numbers. So you're not really responsible for this, writing it in that form. We're just going to do it with coordinates. So here with the b. So for b is 3, 4. We switch it, or we take away 4 from x. So that's minus 4, and we take away 3 from y. And we get negative 1, 1. Then we do the 90 degree counterclockwise. So we switch the coordinates and put a negative on the first one. So 1, negative 1, then put the negative on the first one. So it becomes negative 1, negative 1. And that is the coordinates of e, which is exactly what we want. So this is the coordinates of e, and therefore this is the transformation that we want. Okay, and I'll leave it to you as an exercise to verify that c maps to f and a maps to d with these transformations. All right, so which transformation or transformations can be applied to show the two figures are congruent? Again, I believe we had seen this example. But this time, this time it looks like they're giving you, we're going to select all that apply. Okay, so before we did this, we actually just wrote the transformations down. This time we are just selecting from a list here, appears. Okay, so in this case, we know that, so let's see what happens. So last time we said that we could translate this and then we can reflect it, right? So we're going to see if there's another way to do this. Okay, so yeah, we kind of already figured this out. So what we did is we going back to what we did, we took this, right, and we translated it up 3, 1, 2, 3, and then we moved it so that we want to move it so it's the same distance away from the y-axis, so that when we reflect it, it'll match up nicely. Or you can think about, yeah, so that's what we end up doing. So 1, 2, 3, and then this is 1, 2, 3, 4 away, so we need it to be 4 away here, right? And in order to do that, we would have to move it 1 here. So we'd have to move it 3 up and 1 to the right. If I do that with A, that's 1, 2, 3 up, and then 1 to the right, and then they'll be the same distance here. So you're going to translate it. So translate it, and then follow that up with a reflection, then flip it about the y-axis. Okay, so then we're reflecting about the y, and then we are translating, and that's how we get from the blue to the red. Okay, so example 3, on the set of axes below, pentagon ABCDE is congruent to, and then they have A double prime. This means double prime of the two things. So A double prime, B double prime, C double prime, so on. So we want to figure out how to get from here to here, basically. All right, so let's take a look at the coordinates. So we know that C needs to go to C double prime. So let's start with C. So the coordinates of C are 1, 2, 3. So 3, comma, and then 1, 2, 3, 4, 5. Oh, actually, C is actually at a weird location, so let's not do C. Let's do one that's actually easy to find. So A, let's do, actually, let's not do A because A has pretty easy coordinates. Let's do B. So B is 2, comma, 1, 2, 3, 4, 5. So B, comma, 2, comma, 5. We don't want to do where A has the same coordinates. A is 2, 2. It's really hard to keep track if they're really the same number. So 2, 5. And then we know that, okay, so let's look at example 1, or choice 1 here. A rotation of 90 degrees counterclockwise. So remember the rule for that. I'll write it down. All right, so we're going to use that rule. Using that rule, this turns into -5, 2. And then we're going to follow that up with a reflection over the x-axis. Reflection over the x-axis, if you're reflecting over the x-axis, the y-coordinate changes, but the x stays the same. So the y-coordinate is going to be opposite. So x stays the same, y-coordinate changes. There you go, so -5, -2. Let's see if that works for B. So right now, B prime, the coordinates of B double prime are 1, 2, 3, 4, 5. Yep. And 1, 2, 3, 4, 5. So it's looks like it's -5 and -5, right? Which is not the same as that. So it doesn't look like it could be A. So we're going to go ahead and, or number 1. So cross out number 1. We'll go ahead and do number 2. So 90 degrees counterclockwise. So that means this is going to transform to this. And then we are going to follow that up with a translation down 7 units. So if I do down 7 units, in that case, let me just write down, it should be -5, -5 when we do this. If we do down 7 units, well then we got to subtract 7, right? 2 minus 7 is -5. Does that match up? Yes, it does match up. So that looks to be the transformation. But let's do it with one more, just to be on the safe side. Let's do it with E. E is 1, 2, 3, 4, 5, 2, comma 2. So E is actually, so E is 5, comma 2. So if I do that, if I do the switch and I use this rule, it's going to be -2, 5. Then we'll subtract 7 because we got to go down 7. That gets -2, -2. And that is indeed the coordinates of E here. So this is the correct transformation. This is the best way that I find that to do it, is just to use the coordinate rules and then see if it matches up with the coordinates on the graph. All right, so we're moving on to another benchmark. Determine the weighted average of 2 or more points on a line. So seems simple. So let's look at some examples of that. All right, so determine the weighted average of 2 points. What number W is 3 times as close to 2 as it is to 10? Okay, so there are a couple of ways that you can do this. I'm going to show you the normal way, like the mathematical way to do it, and I'm going to show you sort of the quick way of doing it because it's multiple choice, right? So we'll go ahead and give you both ways. In fact, there's 3 ways that I can show you how to do this, okay? So the first way is okay, so first off, let's go ahead and draw this out. So if I have, so let's say we have a number line, and this is 2 on the number line, and this is 10 on the number line. And it says that there's a number that is 3 times as close to 2 as it is to 10. So that means basically that it's 3 times closer to 2 than it is to 10, is essentially what it's saying. So if it's 3 times closer, then basically what it's saying is that the ratio of distances is 1 to 3, right? So it's 3 times farther away from P as it is to 2. Or in other words, we can say that it's 3 times closer to 2 than it is to 10. That's another way of saying it. All right, so essentially what it's saying is that we have a 1 to 3 ratio from 2 to 10 here, from those 2 coordinates, okay? So this is a partitioning problem, but you can also translate this to a weighted average problem. But let's look at it as a partition. If we look at it as a partition, then we can use the section formula in order to get this. We know that because this is 1 and this is 3, we know that in total this is actually 4, right? 4 parts. So, but anyways, let me just give you the formula for partition. So the formula is nx1 plus mx2 over m plus n. So this is for partitioning a line segment. This is known as a section formula. You can use this. There's other formulas out there, but you can use, this is the one that, is in the book. So in this case, this is m, this is n. You got your x1, you got your x2. So we just plug that in. So if we do that, we get 3 times 1 plus 3 times 2, sorry, the x1 is 2, plus, and then we have 1 times the x2 is 10, over 1 plus 3. In that case, that gives me 6 plus 10 over 4, which is 16 over 4, which is just 4. So we got an answer of 4. All right, so that's method 1. Method 2 is with a weighted average, which is what the benchmark is asking for. But I mean, which regardless of the way you do it, you're going to get the answer. But the weighted average formula is W1x1 plus W2x2 over W1 plus W2. It looks eerily similar to this formula, and that's because it's supposed to be. These concepts are very similarly tied together. In terms of weighted average, the weights are as follows. So because if you think about it, because W is closer to 2 than it is to 10, that means 2 is quote unquote heavier, right? And if 2 is quote unquote heavier, then the weight of 2 must be 3, right? And because W is farther away from 10, that means 10 must be quote unquote lighter. When I mean lighter, I mean in terms of weight, because we're talking about weighted average, right? So if I go to it, go ahead, I don't want to zoom that close. Then the weight for 10 is 1, right? If I use the ratio, okay? So it's sort of reversed, right? So in this case, we got 1, the weight of 10 is 1. So in that case, I got W1 times X1, so 3 times 2, plus W2 times X2. But notice that's the exact same, or W1 is 3, and W2 is 1. You get the exact same thing as this, right? So you get 4 as your answer. So this is in terms of weighted averages. Now here's the quick way of doing it. The quick way of doing it is go through your multiple choice answers, and if I do 4, well, if I try 4 out, well, how far is 4 from 2? Well, it's 2 away. How far is 4 from 10? Well, it's 6 away. Well, then how much farther is, how many times bigger is 6 than 2? Well, it's 3, because 2 times 3 is 6. So therefore, it's 3 times farther away from 10 than it is from 2, and therefore the answer has to be D. So that's another way to check your answer. Okay, so I give you 3 ways to do this. The second way is the actual weighted average, though. All right, so let's do one where we actually use the weighted average rather than like one that has multiple things. So points A and B have coordinates A and given by A and B, they give you the coordinates. Find the coordinate of point P, the weighted average of points A and B, in which point A has a weight of 4 and point B has a weight of 3. So clearly they give you the weights, right? So we're going to call this x1, y1, x2, y2. Those are for my 2 coordinates. And we know that since A is x1, y1, we're going to say that the weight of A, which is W1, is 4, right? And the weight of B, which is W2, is 3, right? They give you the weight here. Okay. So then if we calculate the weighted average, remember we have x and y. So we got x equals W1 x1 plus W2 x2. And we only got 2 coordinates, so we only had to do this for 2 guys. If we had 3 points, we would continue and do this dot, 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 right? Over W1 plus W2. This is how you do weighted grades. If you're doing weighted GPA, you multiply the weight times the grade that you have in that category. And then you divide, you add the weights, divide them, so on and so forth. So this is how you calculate X, and then we'll do this for Y as well. W1, Y1, W2, Y2. All right, so all you gotta do is just plug and chug. So we got 4 for weight 1 times -4 for x1, that's this coordinate there, plus W2 is 3 times x2 is 3 over 4 plus 3. And then for y, the y coordinate is 4 times the y1 is 2, plus 3 times y2 is -6 over 4 plus 3. All right, and then you just do the math here. So we got negative, this is -16 plus 9. -16 plus 9 is -7. And then 4 plus 3 is 7. So -7 divided by 7 is -1. And then we do this for y. This is 8 minus 18 over 7. That's going to give you -10 over 7. So there's your y coordinate. So there you go. So your coordinate is -1, -10 over 7. That's how you straight up do the weighted average with the weighted average formula. All right, let's look at one more example. That last example was a two-dimensional example, so we had x and y. This is a one-dimensional example, so we only have an x coordinate. This is just x, right? There's no x, there's no y coordinate. So it makes it a little bit easier, but now here, we're trying to find the missing weight. So we don't know what w is, right? So if p is 2/3, so p is 2/3, so it's like here. This is like where p is, right? That's where P is located. It says point B has a weight of 2, so we're going to call a point, this is going to be W2 because point B is like the second coordinate. Point C is the third point, so we're going to call that W3 for weight of 4. And we want to find the weight of A, so W1 equals question mark, right? So we don't know what that is. But we do know the x coordinate of A is -4. We know the x coordinate of B is 1. And the x coordinate of C is 4. And we know the coordinate of P is 2/3, so that's going to help us later. All right, so here, let's write down the formula. The weighted average formula is x equals W1 x1 plus W2 x2 plus W3 x3, because we have 3 points, over W1 plus W2 plus W3. And we know x is 2/3 because that is the point that they give you for the weighted average. So that's actually the weighted average that they gave you there, point P, okay? So that's actually 2/3. So we're going to replace that with 2/3. So we got 2/3 equals, and we know W1, we don't know what W1 is, but we do know x1 is -4. We know W2 is 2, x2 is 1. W3 is 4, x3 is 4, over, we don't know W1 again, so W1 plus 2 plus 4. All right, so let's do some math over here. So we got 2/3 equals -4W plus, now this is 2 and this is 16, so that gives me 18. And then we have, this is going to be 6 right here. So W1, or W, yeah, let's just call this W1. W1 plus 4. All right. So what we're going to do is we have two fractions that are equal to each other. So in algebra, what we would do is we would cross multiply. Okay, so we're going to cross multiply these two things. So this times that equals this times that. Cross multiplication. So we got 2 times W1 plus 4. We're just going to distribute. 2 times W1 is 2W1. And then 2 times 4 is 8. 3 times -4 is -12. W1. 3 times 18 is 54. All right, solve for W1. This is a bit of a pain. You know, they give you a lot of algebra here that you need to do. But it's not too bad if you're okay with your algebra. I'm going to add the 12W, then I'm going to subtract the 8 over, and that'll remove that. So 54 minus 8 is 46. Divide by 14, and we get a nice number, thankfully. We get 4. Maybe it's not. No, it's not. That's not nice. It's not a nice number. But we can divide this by 2. Let's just divide it by 2. It gives me 23 over 7. So there's my weight. 23 over 7. Okay, so yeah, there's a lot good that goes on to that problem. So that's I would say the more advanced of the weighted average examples. That's probably the most advanced, or one of the ways they can get the most advanced. All right, so we're moving on to the next topic. Given a mathematical context, use coordinate geometry to classify or justify definitions, properties, and theorems involving circles, triangles, or quadrilaterals. All right, so here we haven't touched quadrilaterals yet, so we're not going to be looking at those. We're not going to look at circles. We're just focusing on triangles, all right? All right, so use coordinate geometry to determine the type of triangle formed below. All right, so we want to determine what kind of triangle is it. Well, first off, is it equilateral? Well, equilateral means all the sides are congruent. Isosceles means two sides are congruent. Scaling means none of the sides are congruent, right? And then we want to determine whether it has a right angle, and if it doesn't have a right angle, is it acute or obtuse, all right? So let's go ahead and determine if the side lengths are the same. Let's figure out the length of AC. So to figure out the length of AC, you need to count up and over. So how much is it up, going up? So it's going one over, one up, and 1, 2, 3, 4, 5 over. All right, and then remember, to get the length of AC, now that you know these two sides, you can use the distance formula or Pythagorean theorem, same thing. You get 1 squared plus 5 squared, take the square root. We're going to do the same thing for AB and see what we get. So AB equals square root. So we got to go 1 over, and then we got to go 1, 2, 3, 4, 5. So they have to be congruent because they have the same sides, 1 and 5, 1 and 5. So these two are congruent, all right? So I'm going to say that these are congruent for sure. Now let's go ahead and do CB. Let's see, 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4 up. So if I do CB or BC, I get square root 4 squared plus 6 squared, which is clearly not the same. So these two are congruent, right? They're the same, but it's not congruent to BC. So therefore, this is an isosceles triangle, right? Two sides are congruent, and the other side is not congruent to the other two. All right, so is it a right triangle? Well, in order to establish that, we need to find the slope. So the slope of AC, remember that slope is rise over run. So remember that we just did it. It went up 1 over 5. So the slope is 1/5, rise over run. And then if we do the slope for AB, well, it's went 1 over and 5 down. 5 down means negative, so the slope is negative. Remember, it's rise over run, so it's the -5 goes first, and then the run is 1. So these are definitely perpendicular because they're negative reciprocals. All right, so because if I flip this and then I change the sign from positive to negative, I get the slope for AB. So these are perpendicular, which means that this is a right angle, which means that this is a right triangle. And if it's a right triangle, it cannot be acute or obtuse. So the only choices are B and C. All right, so let's look at the next example. The vertices of triangles DEF are given. What type of triangle is triangle DEF? All right, so you can graph it, you can figure out the distances, this and that. What we're going to do is we're just going to calculate the distances, and then we're going to calculate the slopes to see if it's a right triangle or not. Okay. All right, so so let's go ahead and look at the distances. Let's calculate DE. Remember that the distance formula is given by x2 minus x1 squared plus y2 minus y1 squared. Take the square root of that. So that's the distance formula. So if I apply that to D and E, I got to subtract the 2x coordinates and then subtract the 2y coordinates, right? So I take the square root, subtract the 2x coordinates, 1 minus 16 squared, subtract the 2y coordinates, 19 minus -1 squared. But a double negative turns this into positive, right? This double negative here turns into positive. So I got square root of 1 minus 16 is -15. And then 19 plus 1 is 20, so we got 20 squared. And then we're going to try to figure out what that is on the calculator. So we know 15 times 15 is 225. And then 20 times 20 is 400, so it's going to be 625. And the square root of 625 is actually a nice number. It's actually 25. If I do 25 times 25, I'll double check that, but I'm pretty sure that is a perfect square, and it is. All right, so DE is 25. That's the length of DE. So now let's do the length of DF, and then we'll do the length of EF. All right, so DF is the square root. So now let's just focus on DF. Subtract the x coordinates, subtract the y coordinates. 1 minus negative 8 squared plus 19 minus negative 8 squared. This turns into plus, so 1 plus 8 is 9, 9 squared. This turns into plus, so that's 19 plus 8 is 27. All right, so we got ourselves 81 plus 27 squared is 810. Yeah, 810. And then the square root of 810. Yeah, so this is going to be the square root of 810, which is about 28.46. This is on the calculator. All right, so let's do EF. So EF. So by the way, this indicates that it's not equilateral because the sides have to all be the same for equilateral, and this is clearly not the same. All right, so now let's look at EF. So the square root of 16 minus negative 8 squared plus negative 1 minus negative 8 squared. So this turns into plus, this turns into plus. So we get 16 plus 8, that is 24. Negative 1 plus 8 is 7, so we got 7 squared. And then we got, so let's go ahead and do that, 24 squared plus 7 squared, that's 625. So lo and behold, it matches up with DE. So this matches up. So it has to be isosceles. All right, what type of triangle is it? Isosceles. Let's verify that it might be a right triangle. So let's verify that. So we're going to find the slope of DE and EF to see if it's perpendicular. All right, and then that'll tell me whether it's a right triangle or not. Okay, so let's do that. The slope of DE, it's a rise over run, right? So remember, to calculate the rise, well, we just kind of so let me just erase this so I can calculate the slope. I'm going to erase this middle one. Okay, so the slope of DE is so to calculate slope, let me put the formula for slope. It's y2 minus y1 over x2 minus x1. So that's how you do the rise over run. Now keep in mind, we've already done that here. This is y2 minus y1, but we'll just do it again just to show you the work. Okay, so DE. Y2 minus y1, so negative 1 minus 19 over, now we're going to do 16 minus 1. So we get negative 20 over 16 minus 1 is 15. So we got negative 20 over 15. Let's go ahead and calculate. Oh yeah, and then let's reduce this. So this is going to reduce to negative 4/5. Divide top and bottom by 5, you get negative 4/3. All right, so now let's do the slope of EF. So rise or run, so, or y2 minus y1. So y2 minus y1, negative 8 minus negative 1 over x2 minus x1, negative 8 minus 16. So I get negative 7 over negative 24, which is the same thing as positive 7 over positive 24. So this is definitely not the same, or not a reciprocal of this. So it cannot be a right triangle. It cannot, because it's not a reciprocal or anything like that. So it has to just be an isosceles triangle. And we are done. All right. So let's look at example 3. Use coordinate geometry to classify the following two congruent triangles. Same idea as it was before, using the distance formula and all that. So again, let's do AB. Let's just do all of the sides. So AB is equal to the square root of, let's count it, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. This is 6. So the square root of 4 squared plus 6 squared. Counting it saves us the trouble of having to subtract and all that, but you can do either way. And this is going to be 16 plus 36, which is 52. All right, and then we'll do BC next. The square root. So BC looks like it goes 1, 2, 3. Let's make sure we count it. 1, 2, 3 down, 1, 2 over. So we got square root of 3 squared plus 2 squared, which is the square root of 9 plus 4 is 13. Just do that on the calculator if you're having trouble with that. And then you got AC, so it goes 1, 2, 3, 4 spaces here, 1, 2, 3, 4, 5, 6, 7 spaces here. Again, just subtract the -9 minus -2, that's going to give you 7, right? Plus 7, oops, wrong one here, sorry. CA equals square root 4 squared plus 7 squared. So you got square root of 16 plus 49. 16 plus 49, that is 565. So 65. Okay, and then we're gonna do the other ones, DE. So we're gonna do it here. So DE is 1, 2, 3. And then 1, 2, 3, 4, 5. So 3 and 5. Square root of 3 squared plus 5 squared. So in that case, 3 and 5, that's 9 plus 25 is 34. Already, none of these match up, right? So far, not looking good as far as equilateral or anything. So it cannot be equilateral. Let's see if it's isosceles. It might be scaling. Let's see. So let's do DF. DF is the square root. So it looks like, let's count it. It's going up 2, and it's over 1, 2, 3, 4. Oops. 1, 2, 3, 4, 5, 6, 7. So square root of 2 squared plus 7 squared. Square root of 4 plus 4, 49. That's 53. All right, very, very close to 52, but not close enough. And then let's do the last one. Let's just see if it's if there's one of them that match up. So 1, 2, 3, 4. 1, 2, 3. So it's going to be EF is square root of 4 squared plus 3 squared, which is square root of 25. So none of these match up. So it's going to be, yeah, so they're all scaling. They're both scaling basically, right? And if you look at the slopes, none of them are reciprocals of each other. You can see that this is not a reciprocal of that, which is not a reciprocal of that. So it's not even going to be right. It's just going to be looks like acute triangles. Okay, you can see that they're you can see that they're going to be acute triangles here. All right, so if it's not right, definitely going to be acute. So let's take a look at all right, hold on, let's see. All right, so let's look at the next problem here. So use coordinate geometry to solve mathematical and real-world geometric problems involving lines, circles, triangles, and quadrilaterals. We're just focusing on lines and triangles here because we haven't gotten to circles and quadrilaterals. We'll get to that in the new year, the second semester. All right, so here in this example, since they're talking about theorems of lines, this includes partitioning. So we went over the formula for partitions. If you have a partition, you're going to, the formula that we used in the textbook is the section formula, which is, I'll write it here again, is nx1 plus mx2 over m plus n. And then there's the y version, ny1 plus my2 over m plus n. You can tell this is a partitioning problem because it gives you a ratio. What are the coordinates of point R on QS such that the ratio of from QR to RS is 2 to 3? So this is your ratio. So this is m, this is n. Okay, m is 3, n is 2, m is 2, n is 3. And then your x1 and x2 are your coordinates for Q, right? So the coordinates for Q are -6, -2. This is your x1, y1. Your coordinates, and we know Q is x1, y1 because you're going from Q to S, okay? So S has to be x2. So we got 5 and 6. So this is x2, y2. So all you gotta do is plug it in, get your answer. So we got x equals, n is 3 times x1 plus 2 times x2 over m plus n. I'm going to do the same thing for y. Y equals 3 times y1 is -2 plus 2 times y2 is 6 over 2 plus 3. All right, just do the math. This is -18, this is 10. If I add those together, I get -8. 2 plus 3 is 5. All right, and then and -8 over 5 is -1.6. If I do this for y, I get -6 plus 12 over 5, which is 6 over 5, which is 1.2. So those are my coordinates, -1.6 and 1.2. So it's A. All right, so example 2, find the center coordinates of the circumscribed circle of the right triangle, triangle OAB. I will tell you, according to the blueprint, I did not see any indication that there will be circumscribed circles or anything like that on the midterm. However, you never know, so I want to include this question just in case. They may definitely include that in the EOC, but as far as the cycle 2 blueprint goes, since this was like the chapter we covered just before the midterm, I don't think they ended up including it, but just in case. The circumcenter, if you recall, if I have a triangle, the circumcenter is obtained by taking the perpendicular bisectors of the sides of the triangle. So if I take this side and I do the perpendicular bisector of it, that's the side, that's the where it goes at a right angle and it cuts the side in half. I do this for all the sides. So if I do it for this side here, the perpendicular bisector is going to be a right angle and it's going to cut that in half. And then I repeat that for this side here. I gotta go cut it at a right angle and then cut this in half. Then if I do that, they're gonna cross at the same point. Those perpendicular bisectors will cross. And that point that they cross is called the circumcenter. And that is the same distance from each of these points on the vertex. It's the same distance from each of these points. And then I can draw a circumscribed circle, which is a circle that goes around the triangle. So that's what they mean by the center coordinates of the circumscribed circle. So we want to find that, okay? So if I look at this, well, then half of this line is at 2, right? So, and if I cut it in a perpendicular, that's right here. That's the perpendicular bisector, this line here. Then if I look at this side here, half of that is like here, right? So then if I cut that in half at a right angle, then there's my perpendicular bisector. Next, I'll do this side here. Well, that's this point. This is half of that. If I cut it at a right angle, it'll look, it might look something like that, right? Well, then in that case, they all cross here, right? So this is my circumcenter, or my circumcenter. So that's going to be 2, 3. Looks like 2, 3 for my coordinates. All right, so the answer is B. All right, so that's what they're looking for. So for example 3, points A, B, and C are collinear on line segment AC, and the ratio of AB to BC is 3/4. A is located at XY, B is located at 4,1, and C is located at 12,5. What are the values of X, Y? So just to kind of give you an idea, just a quick picture. This is A and this is C. C is located at 12,5. This is not drawn to scale or anything like that. It's just as a picture, a visual. We know that we don't know the coordinates of A, but we know that B is located such that from A to B is closer than it is from B to C, right? So it's 3-to-4 ratio. So that means it's actually closer to A than it is to B. Than it is to C, sorry. So B is closer to A than it is to C. There's my 3-to-4 ratio from AB to BC. So because we got the drawing, now you can kind of see what we can do. We can either use the X coordinate or the Y coordinate. Actually, we're going to try to find X and Y. That's what they want us to do. So we're going to need to do both of them. So if I use the section formula, which I will, let's call this x1, y1, and then this is x2, y2. So essentially what we're trying to do is find x1, y1, right? And then we know that this is m and this is n, right? The 3-to-4 ratio. And we can use the section formula. So we can say x equals, let me write the section formula one more time just to jog your memory. So if I do that, well, then we know that x is equal to the coordinates of B, right? So the coordinates of B are 4, 1. So this is going to be x. This is going to be y. And this is not to confuse. This is not to be confused with this x and y. So what I'm going to do is I'm going to call this x1, y1. All right, just so that we don't confuse it with the regular x, regular y. So let's call that x1, y1. Okay, and that's what we're trying to find for A. That way we don't confuse it. So in that case, we know that the regular x is 4. So 4 equals n is 4. X1, we don't know. That's what we're trying to find. And then x2 is 12. So we got to do, here, since I'm running out of room here, let's just call this x and y. I want to make sure we have enough room here. All right, so we said x was 4, so 4 equals n times x1 plus m times x2, which is 12, over m plus n, which is, so that's what we get. And so this is 4x1 plus 3 times 12 is 36. 3 plus 4 is 7. We're just going to clean that up. So we got this is equal to 4. All right, so now what we can do is we can solve for x1 here by multiplying both sides by 7. That way we can get rid of it. That's the only way to get rid of that denominator. So we can multiply by 7 on both sides, so this turns into 28. So we get 28. Let's do that over here. 28 equals 4x1 plus 36. So if I subtract 36 on both sides, that gives me -8. And so x1 has to be -2. So we got the coordinates of x1. All right, so which is what they want to hear. All right, so x1 equals -2. Let's do y1. All right, so remember the formula is y equals nx1 or ny1 plus my2. So let me write the formula down. So we got y equals ny1 plus my2 over m plus n. But we know y is 1. So we got 1 equals 4 times y1 plus m times y2. y2 is 5 over 3 plus 4. All right, so we get 1 equals 4y1 plus 15 over 7. Again, let's multiply both sides by 7 to cancel that out. And that gives us 7 equals 4y1 plus 15. Take away the 15 to get -8. And looks like y1 also equals -2. So the coordinates are -2, -2. All right, so that was a pretty, that was definitely a more complex example, but again, I wanted to include problems of different levels. So here we go. So there you go. All right, let's look at one more partitioning problem. This is like the one that's, partitioning is one of the ones that students struggle with the most, which, if you have the formula, you really can't go wrong, but some of these can be tough. So it says M is located at -3, -5. T is located at 1, -3. And D is located at 9, 1. What is the value for the ratio MT to MD? Again, it's good to have a visual. So we want MT to MD. So this is M, and let's say this is T. And then we have D. So M is -3, -5. T is 1, -3. D is 9, 1. So T is somewhere in between them. We need to know what the ratio is. We need to know what these numbers are, like what ratio is it, right? Is it a 3-to-1 ratio? Is it a 1-to-1? Whatever. So what we're going to do is we're going to try to find M and N here. So the best way that I found to actually do this is just focus on one of the coordinates. So let's just focus on X, okay? So if I just focus on the X coordinate, right? Let's just focus on the X coordinate. You can pick either X or Y, but just focus on the X coordinate. Well, in that case, M is at -3, T is at 1, and D is at 9. If I just look at the X coordinate, right? And then how far away is -3 from 1? Well, it's 4 away, right? 4 units. Subtract them, you get 4. -3 minus 1 is -4, but we're just looking at the number, the absolute value, which is 4. Okay, so again, what I did is I just subtracted them and did the absolute value. And then how far is 1 from 9? Well, if you do 9 minus 1, then do the absolute value, you get 8. So they're 8 away. So there you go. So it's 4 to 8. So from M to T is 4, from T to D is 8. So it's a 4 to 8 ratio. So the ratio, let's do MT to M. Oh, and we want MT to MD, so we want to be careful with that. So we also want to be careful of what they are asking in the question. So well, MT to MD. Well then, okay, well MT is 4, right? And MD is this whole thing, right? From M to D is 12. So it's actually 4 to 12 ratio. So be very careful with what they're asking for. So in this case, 4 to 12, that is, if we reduce that, that is a 1 to 3 ratio. So you could say 4 to 12 or 1 to 3. And that's really all there is to it. If you did it for the y coordinate, you're going to get the same answer. All right. So let's look at the next benchmark. So use coordinate geometry to solve mathematical and real-world problems involving perimeter and area of polygons. All right, so find the perimeter and area of the figure. Each unit is 1 meter. Round answers to the nearest tenth if necessary. All right, so okay, so we're gonna do the perimeter. Let's see the perimeter. Remember, the perimeter is when you add up all the sides. So we can count this here easily. Distance from here to here, if you count that, that's 8 spaces, 8 units. From here to here, that's 4 units. And then in order to calculate this, remember, you're going to need to do the distance formula. So that's the square root of, well, first you're going to need to count it. So how much does it go up and over? Well, we know it goes up 8 and over 4 because we just counted that, right? This is up 8 over 4, so we just did that. So we know this is going to be the square root of 8 squared plus 4 squared. So that's going to be 8 times 8 is 64. 64 plus 16. If we add that together, that's 80. So this is going to be square root of 80. Okay. So And that's going to be a decimal, so let's figure out what that is, because we want to round to the nearest tenth, right? Square root of 80 is almost 9, right? Because 81 square root of 81 is 9. So let's do 80 and then do the square root of that. We get 8.9, makes sense, to the nearest tenth. So we get 8 plus 4 plus 8.9 is 12 plus that's 20.9 units. All right, so there's your perimeter. And then to find the area of a triangle is 1/2 base times height, where the height and the base have to be perpendicular. So the height and the base need to be at a right angle to each other, which they are here. So this is a right angle. So we know we got our base, we got our height, so we can just multiply them and divide them by 2. So 1/2 times base of 4 times height of 8. Half of 4 is 2, and then 2 times 8 is 16. So 16 units squared. There's our perimeter, there's our area. Okay, so this one is an interesting problem because there's a lot going on in this. So we're going to take a look at this. There's different shapes here. There's different concepts that we want. So okay, so let's take a look. So Monica is redesigning her backyard. She has created the following blueprint to model her design. She wants to have at least 300 square feet of grass available in the backyard for her dog. Is there enough space for her dog? If there is, then how much area is available? Okay, so we're going to say yes or no if there's enough space, and then we're going to calculate the space that there would be for the dog. So, all right. Well, first off, we know that she needs 300 square feet, so we're going to need to figure out the area of this grassy portion, right? Which means there's a lot of things we want to know. We want to know the area of the circle. We want to know the area of this garden. And obviously, we're going to need to know the area of this portion here, right? So we're gonna break them up into shapes that we to normal shapes, and then find the area of those shapes, and we're gonna use that to approximate. So if we look at this first off, let's take a look at the area of the lot including the house. So what's the area of the entire lot including the house? All right, so the area, the total area, we're gonna call it total area of everything. Well, it's a square, right? So it's base times height. We got the base, we got our height. Our base is 30. This is 30 right here, and this is 30 as well. Okay, so the area of that entire part is 30 times 30 is 900 square feet. So they have 900 square feet, including this house portion, right? Which is not a lot of square footage. It's a little bit of square footage. So we want to make sure that we have enough space for the dog, because that's important. So now we're going to do the area of the circle. So remember, the area of a circle is pi r squared, right? So pi times r squared. Now the radius of the circle, this is the center of the circle. And we can kind of tell because, well, let's see. Let's just measure this out. From here to here, how far is that? From there to there, it looks like it's going from 4 to 12. So the distance here is 8, which means the center is here and the radius is 4, right? The radius has to be 4 for that circle. So we have pi times 4 squared. And 4 squared is 16. So we got 16 times pi. So 16 times pi. We can use 3.14 for pi, I guess. And that's 50.24 square feet. So it's a little portion for that little fire pit, but we got to take away that area because that's area that we're assuming the dog is not going to have enough space in, right? So we're going to take away that space because the dog is not going to be there. We want the grassy part for the dog, right? So that's what we're going to do. All right, so we got that. Now we're going to do this portion, which we can split it into this rectangular portion and then this rectangular portion for the garden. So we got two rectangles here. The area of this rectangle is, well, base times height. The height here is from here to here is from 30 to 26. Remember, these are going by twos. So it's actually 4 feet here. And from here to here, if I count it, there's, well, it's going from, yeah, it might be actually easier. Okay, so yeah, if I look at it, it looks like it's, yeah, so this looks like it's halfway between here and here. That looks like it's halfway, right? So if I trace it down here, that's halfway between 26 and 28, so that has to be at 27, right? So that's at 27, and this here is at 20. And so the distance here must be 7, right? Okay, so this has to be 7. So the area of that rectangle is 28, because 4 times 7 is 28. All right, so area, we're going to call this area number 1. So area 1 is 4 times 7 is 28. Okay? And then we're going to call this area 2 for this garden. So this here is from 27 to 30, right? So 27 from 30, that's 3. This is 3 feet. And then from here to here, it's 2, 4, 6, 8, 10 units. So 3 times 10 is 30. So area 2 is 30. 3 times 10 equals 30. Okay, so we're going to take all of that away. Let me delete this now so we don't have too many numbers on the board. So we got those. Now we need to subtract, of course, this portion here, which consists of a lot. There's this trapezoid part, right? And then there's this rectangular portion. Okay, so we're going to do the rectangle portion and then the trapezoid. Let's do the rectangle portion first, and we'll call that number 3. And then we'll do the trapezoid, we'll call that number 4. All right, the rectangle is easy. This is 30, and then this is 10. So 30 times 10 is 300. So that's area 3. 30 times 10 is 300 square feet. And then we need to do the area for the trapezoid. The area of a trapezoid, I'll write it over here. The area of a trapezoid is 1/2 times height times base 1 plus base 2. All right, this is base 1, this is base 2. The height is the height of the trapezoid. So let's figure out what the height is. The height is going from 10 to about, this is about 15 right here. So it's going from 10 to 15. So the height is 5. All right, so area of 4 equals 1/2 times 5 times base 1. How long is base 1? This is going from here to here, so it's going from 2 to 18. So that's 16. So we got 16 plus, and then base 2 is going from 0 to about 20, so that's 20. There's your area. So we got 16 plus 20 is 36, divided by 2 is 8. 18 times 5. We're just doing this. You could do this on the calculator. This is 90 square feet. All right, so let's go ahead and do the math. Let's add these up, and then we're gonna subtract that from, yeah, let's add these numbers and then subtract that from 900. Okay, so 900 minus those numbers, all right? And that will give us our area that's left over for the dog. 900 minus 50.24 minus 28 minus 30 minus 300 minus 90. All right, so it looks like we got 401.76 square feet. So we do have enough space for the dog, apparently. It looks like we do. We have greater than 300 square feet. So it looks like the dog will have enough area to roam around. Okay, so let's do, this should be, I think, the last one. There might be, yeah, that should be the last one in that benchmark. So let's finish it off. This is the trapezoid. We just looked at a trapezoid before. We could, and we're just doing the perimeter. So let's go ahead and do the perimeter. So for here, we're going to add this together. Remember, we're adding all the sides. So in this case, from 1 to 12, that's a distance of 11. So this is actually 11. So AD equals 11. All right. Now for CD, we have to count it. That goes 1, 2, 3, 4 spaces, and then we got 1, 2, 3 spaces. So we're going to do CD equals square root of 3 squared plus 4 squared. And that's 3 squared is 9, 4 squared is 16. Add those together to get 25. And the square root of 25 is 5. So that's a nice number, CD. And then BC is 1, 2, 3, 4, 5, 6, 7 spaces. So BC is 7. And then we'll do AB. We got 1, 2, 3, 4. And we got 1 here. So AB equals square root 4 squared plus 1 squared. So that's going to be square root of 17. All right. And square root of 17 is approximately 4 because 4 times 4 is 16. But we'll get that as a decimal. That's about 4.1. All right. So the perimeter is 4.1 plus 5 plus 11 plus 7. We're just adding all 4 sides. So that's 9, 20.1. So 27.1 is your perimeter. All right, so let's look at the next topic, solve mathematical real-world problems involving volume. Okay, so now we're doing volume. All right, so which solid has a greater volume? A cone with a base radius of 7 and a height of 28, or a pyramid with a base area of 154 and height of 28. Okay, so formula for the volume of a cone is 1/3 pi r squared h, okay, where h is the height of the cone and r is the radius. The formula for the pyramid, for a pyramid is 1/3 capital B times capital H, where B is the base area and H is the height of the pyramid, okay? So if you got your pyramid, your base area, that's your capital B. And your height, that's your capital H, all right? Now they give you the base area, so they give you that. They give you capital B, they give you 28. So they're saying that capital B is 154. They're saying that capital H is 28, all right? Now in the cone, they're saying that the radius is 7 and the height is 28, okay? So the height for both of them is 28. All right, so we got 1/3 times pi times radius squared times height. And then for the pyramid, 1/3 times 154 times 28. Then you just got to compare it to see which one's biggest. So you get 1/3 times pi times 49 times 28. Let me just figure out what that is. We'll do it all in the calculator and see what we get. We're going to use 3.14 for pi here. So for the cone, we get 1,436.03. For the pyramid, let's see what we get. 1,437.33. So it looks like the volume of the pyramid won out is actually slightly greater than that of the cone. So the answer is B, pyramid. All right. So Tiankang is a hole with nearly vertical walls. The Tiankang is approximately cylindrical with a diameter of 180 meters. Forgive me if I butchered that. And a depth of 420 meters. It's cylindrical. So we got ourselves approximately a cylinder. The volume of a cylinder is pi r squared h. Okay. So in that case, and the radius, they said that the diameter is 180. So if the diameter is 180, that means the radius is half of that, right? So it's 180 divided by 2. The radius is 90. Okay, so we got to plug that into there. And then the depth is 420. So that's like the height. So we know that the height is 420. All right, so we got the volume as pi times 90 squared times 420. And that will be the volume of water that it could fill. So 90 times 90 times 420 times pi, 3.14. 10,682,280 cubic or square meters, or no, cubic meters of water. That's a lot of water. All right, so there's the volume of water. All right, so a cylindrical trash can is 30 inches high and has a base radius of 7 inches. The manufacturer wants to know the surface area of this trash can, including the top of the lid. So we're not going to do the surface area here because that's not what this benchmark is testing. And when we do surface area in the next benchmark, we'll probably end up doing this surface area problem. But for now, we're just sticking to volume because that's not what the benchmark we want. We want the volume, which is what the benchmark is looking for. So the volume of the cylinder is pi r squared h. So we have pi times 7 squared times the height is 30. And you just multiply those, get your answer, round to the nearest square inch. It shouldn't say square inches, it should say cubic inch because we're doing volume. So that's a typo. So we have 49 times 30 times 3.14. So we have 4,615.8-ish cubic inches. So inches cubed. All right. Okay, speaking of which, now we're doing surface area. So we want in surface area and three-dimensional figures. So let's do the surface area. In the model of the solar system, Earth and Mars are spheres where Earth has a diameter of 15 inches. So D is 15. So we got to convert that to a radius. Radius is half of that, so 7.5. That's for Earth, right? So this is for Earth. Mars has a diameter of 8 inches, which means that the radius is 4 for Mars. How much greater is the surface area of this Earth model? Well, the surface area of sphere, right, is 4 pi r squared. In that case, we got 4 pi times r squared is 7.5 squared for Earth. Let's say this is SAE for Earth. This is going to be SAE for Mars. So we have 4 pi times, let's do E for Earth, radius of Earth, and this is radius of Mars. So we got 4 pi times 4 squared. And we just got to, and then what we're going to do is we're going to take the difference. We're going to subtract those once we find out what they are. So we have 4 times that. So this is 706.5. Oh, we want it in terms of pi, so I'm not going to plug in 3.14 for pi. I'm just going to leave pi alone, just put it off to the side. I'm going to multiply 4 times 7.5 squared. So if I do that, I get 225 pi, okay, for the surface area of the Earth model. And then this is 16 times 4, so that's 64 pi. And then we're going to subtract them because we want to see how much greater is the surface area. So 225 minus 64, that's 161, and then pi. All right, so example 2, again, same problem, but same scenario, but this time we're doing the surface area, okay? So what is the surface area available for plants? If the top of it is open and plants can grow on the bottom and the sides. So in this case, it's open on here, right? So this is open, but here it's closed. So we can actually, I mean, it's the floor, so obviously it's going to be closed here. And then, so we're just finding the surface area of everything else except for the open top part of it. So the surface area of a cylinder is normally you take the surface area of the bottom plus the surface area of the top plus the surface area of around it, right? However, the surface area of the top and the bottom is both pi r squared because the area of a circle is pi r squared. So normally the surface area is 2 pi r squared plus, and then this portion right here, the side portion, is 2 pi times r times h. However, because it's open on the top, we're going to get rid of this area. We don't care about that. It's open. So therefore, instead of this being 2 pi r squared, it's 1 pi r squared. Okay, so this is the surface area if it's open at the top. Okay, so they give you the formula for this, but you just got to be aware because you're not doing the top, you're going to get rid of that. So it's going to be pi r squared instead of 2 pi r squared. All right, so we got pi times the diameter is 180, so that means the radius is 90. So we got 90 squared plus 2 pi times 90 times the depth is 420. All right, and then we'll figure out what that is. Let's do 3.14 for pi, of course. I get approximately 262,818 square meters of space. Again, this is not including the top. If we put a 2 here, then it would include the top. All right, so let's look at another one. Find the surface area of the pyramid given, include units. So pretty simple problem. Just you know, they give you a pyramid, and then you just got to find the surface area. All right, so the surface area of a regular pyramid is surface area of a regular pyramid is 1/2 P times L plus B, where B is the base area. P is the perimeter of the base area. I guess you could say the base area or the base, whatever. We'll say the perimeter of the capital B base. And then the L is the slant height of the pyramid. So this is the slant height, is that. And 16 is the slant height. Now the perimeter of this base, we'll find it now. The perimeter is the perimeter of this base. This is the base area, right? This is the base, capital B. So the perimeter of that, well, it's a square, so it's 8 plus 8 plus 8 plus 8, right? So here, let me draw this is the base, which is 8 plus 8 plus 8 plus 8. So the perimeter is 4 times 8 is 32. Now the area of that base, which is the base area, capital B, is 8 times 8, which is 64. Okay, so that's the capital B, is the base area. So we know capital B, we know capital P, we know lowercase l, or script l, so we can plug it into the formula. So surface area equals 1/2 times perimeter times the slant height plus your base. All right, so this turns into 16 times 16, which is 256 plus 64. Add that up. So you get, looks like 320. Let's double check that. Yeah, so 320 square feet. All right, so that's the quick way of doing it. Just use the formula, and then they give you this formula on the EOC, so you might as well take advantage of it and just know how to find each of the pieces, the components. All right, so suppose Martha wanted to paint a container with the given dimensions. Suppose the cost of paint is $25 a gallon. Suppose that 1 gallon is enough to cover 300 square feet. How much will Martha spend to paint the outside of the container? All right. So since we're painting the outside of the container, we're doing the surface area. We're painting the surface of the container. So this is a surface area problem at its core. And so we need to find the surface area of a cylinder and the surface area of the cone. Okay. Now keep in mind that when you do the surface area of the cone, let me go back out of there. I'm zoomed in too much. So, okay, so if I have a cone, the total surface area of the cone is the bottom portion, which is the circle portion, which is pi r squared, plus the side portion, the side part, which is pi r l, right, where L is the slant height of the cone, this slant height here. So that's the surface area of a cone. So yeah, but remember that since we're painting the outside of this container, you can't even, this part right here is inside the container. The bottom of the cone is actually inside the container. So you can't paint the bottom of the cone. So therefore you're going to exclude the pi r squared portion of the surface area. You're only going to look at the pi r l portion. This is the part on the outside of the cone, known as the lateral surface area. So you're only doing the lateral surface area. You're not doing the base area. Okay, So in this case, for the cone, it's pi or L for the cone. For this problem, right? For this problem. And then because you're only doing the outside of the container here, you're not doing the bottom of the container, and you're not doing the top of the cylinder either. So normally for a cylinder, the total surface area is 2 pi r squared. That's because you have the top of the container and the bottom of the container are both pi r squared. So that gives the 2 pi r squared. Plus the outside of the container is 2 pi, or yeah, this outside portion is 2 pi r h. So that gives you the total surface area. We're going to exclude this part because we can't paint the bottom and the top part, assuming that we can't do that. So we just want to do to paint the outside of the container. We don't care. Well, we might be able to paint the bottom, but we're assuming that maybe she doesn't want to paint the bottom. If we include the bottom, I guess we could. Yeah, so assuming that we're just going to paint the complete outside, the lateral part, and not the base, then I'm just going to assume that. In that case, it's 2 pi r h and pi r L. So we're going to combine those together. This is for this cylinder. So in other words, the total surface area in that case is going to be 2 pi r h plus pi r L. So the total is 2 pi r h plus pi r L. All right, so we're just going to combine them, essentially, is what I'm saying. All right, so let's do the surface area of the cone. So the surface area of the cone is pi times the radius of the cone. Okay, so what's the radius of the cone? Well, the radius of the cone is 12 because the radius of the cylinder is 12. They're both the same radius. So we got 12 times, and then the slant height of the cone is 13. This is this guy. So there's the surface area for the cone. Surface area for the cylinder is pi times radius, which is 12, times the height, and we forgot the number 2 here, 2 pi times 12, times the height is 10. All right, let's go ahead and add these together to get the surface area total. All right, let's figure out what this is. So we get 13 times 12 times pi, 3.14. And then we're going to add that to 12 times 10 times 2 times pi. So we get 1,243.44 square feet. All right, so that's the total square footage. And then remember that 1 gallon is enough to cover 300 square feet, right? So we're going to need to divide this by 300. So divide this by 300 feet per gallon, and that will give us the number of gallons, square feet per gallon. So divide that by 300. So that means we'll need about 4.1448 gallons of paint. So a little bit more than 4 gallons. Now we know that it's $25 per gallon. So it's $25 per gallon. So we're going to need to multiply by 25. So it's going to be a little bit over $100. So about $103.62. Okay, and that's just to paint the outside. If we want to paint the bottom, we're going to need a little bit more paint. And actually, now that I think about it, if we multiply this by 25, this will be the exact amount. However, assuming that we can only buy paint in gallons and we can't buy it in pints, it might actually be more than that, right? Because we might have to buy 5 gallons of paint, or maybe 4 gallons and then a pint. But here they don't give us that information, so we're just going to assume that we can get that exact amount of paint, just to not complicate the problem. In that case, that would be $103.62. Okay, assuming we can get that exact amount. All right, so they need to be more specific in that problem in order to answer that question. All right, so let's construct a copy of a segment or an angle. That's the next benchmark here. All right, so construct a copy of a segment or an angle. So this is all about construction, so you have to know the steps in constructing in order to be able to answer these types of questions. All right, so what is the next step in constructing an angle that is congruent to angle A? All right, so notice normally that if you want to do a construction and you want to copy angle A, right? Let's say this is angle A. Well, the first thing you do is you draw this line, you draw this ray, right? That's step one. Next thing you want to do is you're going to draw this, this arc with your compass, right? And then you're going to label these points. And then you're going to repeat that on the other ray. You're going to continue to do this. And then once you do that, you're going to measure this distance and with your compass. And then with that measurement, you're going to put one end of the compass here, the other end, and then with the other end, you're going to use that other end to draw an arc of that same length, right? And then you can connect where those two arcs cross, and that will be the copy of your angle. All right, so that's essentially the steps. So review that in your review the steps. But in any case, the next step here in this construction is to label those points, right? So we're going to label the points where the arc intercepts the sides of the angle. So that's the next immediate step. If they said the next, another step after that would be to just draw that same arc on ray X. Okay. All right, so name the construction. So sometimes they'll give you steps in the construction, images, and then they ask you to name the construction. Okay, so if I look at this construction, this is similar to what I was saying earlier, right? You draw your ray, right? On your angle, you draw this arc. And then you measure that arc with your compass, right? So that's exactly what's going on here. And then when you draw this arc here, and then with the compass, you draw another arc here that's the same measurement, and then you connect. That's exactly what that is. So this is a copy of an angle. All right, so here, example 3, when copying a line segment AB using a straight edge and a compass, the compass should be used to do what? Remember, so if you're trying to copy a line segment, let's say line segment AB, the first step is you draw a line with a straight edge, right? And let's just call this C. And then with the compass, they say the compass should be used. With the compass, you're going to measure the distance from A to B. And then once you have that measurement, you can actually copy that measurement onto here, make a mark, and then that's how you know where your line ends, and you can measure the exact length. So the arc should be used to measure the length of AB. All right, so the next benchmark, construct the bisector of a segment or an angle, including the perpendicular bisector of a line segment. Okay, so this is another constructions benchmark, but this time we're doing bisectors of segments or angles. All right, given the diagram, which of the following must be true? All right, so this is not necessarily like 100% construction. This is just this has to do with perpendicular bisectors, but it's the concept of it, right? So we know that this right here is a perpendicular bisector because it's perpendicular to the line segment QR. It's at a right angle, and it cuts the QR in half. So that's a bisector. That's what a bisector does. So because it's a perpendicular bisector, what we have to do is we have to identify which is true. So it's saying that QR must be congruent to TS. That is not necessarily true because for this to be a perpendicular bisector, it doesn't have to, the length doesn't matter for it. So I could just as well have done this, right, which is shorter, and that's still a perpendicular bisector as long as this is a right angle and this cuts that in half. So it has the same properties as this one, but it has a different length, right? So this doesn't necessarily have to have the same length as this, right? So this is not true in general. TQ is congruent to TR, so they're saying that this distance is the same length as this segment, as this distance. So that is actually true. For a perpendicular bisector, anywhere on that perpendicular bisector is going to be the same distance from the endpoints of the line segment. So then these will also be the same distance, for example, from either end. That is called the perpendicular bisector theorem. So pretty important theorem. B is going to be the correct answer, but I'm going to look at the other ones. QT is congruence to QR. Let's do that. QT is congruence to Q, or QS, sorry. So you may be tempted to say that this is also true. However, this is not guaranteed to be true. This is only guaranteed to be true if QR is a perpendicular bisector. But we have no idea whether QR is a perpendicular bisector. We know that QR is perpendicular because it does cut at a right angle, but we do not know whether these are congruent on either side. So we don't know that it's a bisector. And if we don't know that it's a bisector, there's no guarantee that these are the same length on either side. Because it might be that this is cut in half here. However, it might be that this does not cut this in half, right? So in this picture that I drew, this is actually 5, this is actually 2. There are different distances. So if those are different distances, it's not guaranteed that these are going to be the same distance, right, on either side. So C is not guaranteed. And then similarly for TR, okay? So the answer is definitely B. All right, example 2. Which image shows the construction of a perpendicular bisector? All right, so when you construct a perpendicular bisector, let's say you have a line segment AB and you want to cut it in half and cut it at a right angle. The first thing you're going to want to do is you're going to want to measure your compass from A to a little bit more than halfway through AB. So like if this is halfway through AB, a little bit more than that. So you might be just short of B. As long as you're greater than half of AB, you're going to measure that compass so that it's that amount. And then once you measure that amount, you're going to use that to draw an arc above and below the line segment. And then you're going to repeat that measurement for B, right? So you're going to do this, and you're going to use that to draw an arc below and above. And then when these arcs will cross, and then you can connect them to get your perpendicular bisector, okay? So when you do that, you end up making like something that looks like that, which looks like D, okay? So you end up making these arcs that you end up connecting. So the answer is D. All right, so example 3, choose the construction represented by the given image. This is actually, so if you connect this with this right here, and you connect these, that actually cuts this angle in half. So that's actually a perpendicular, or an angle bisector. Okay, so this is an angle bisector. Let's go over the steps of the angle bisector just to make sure you're aware, because we are reviewing after all. So this is angle P. First thing you're going to want to do is draw an arc through the angle and call these points where they cross, whatever you want to call them. So we're going to call them QR. And then you're going to take your compass. So you're taking your compass and you're drawing this arc. So that's the first thing you want to do. Then now that you have Q and R, you're going to take your compass and you're going to draw an arc inside the angle QPR. Then you're going to take your same compass and then put your end on R instead. Do the same thing, but you're going to do it from R. Okay, so from R you're going to draw an arc, and it's going to go like this, right? And then where these arcs cross, you can connect it to the vertex of the angle. That's your angle bisector. All right, so those are your steps essentially. All right, so next benchmark. Identify and accurately interpret if, then, if and only if, all and not statements. Find the converse, inverse, and contrapositive. Okay, so first off, let's go over what these are before we do the next question. So converse. So if-then statements are usually written in this general format. If P, then Q. So that's called a conditional statement. That's an if-then statement. So if P, then Q. Or P implies Q. If I wanted to do the converse of this statement, this is the original statement, the original conditional statement. If I wanted to do the converse, then I would have to, this is known as the hypothesis, and then this is known as the conclusion. So to do the converse, I need to swap the hypothesis and conclusion. So I need to switch them. So it turns into Q implies P. That's the converse, is you switch the statements. So converse is a switch. Inverse is you take the original conditional and you negate it. So you do the opposite of it. So not P implies not Q, where this not operation means you're going to do the opposite. And then contrapositive is you do both. So you do the inverse, and then once you do the inverse, you do the converse of that. So you switch it. So not Q implies not P. All right, so this will make sense once we do the example. So the conditional is if an angle measures 100, then it is obtuse. This is like P, this is like Q, right? So if I switch them and do Q implies P, right? I switch it, so then I say if it is obtuse, then it must measure 100. So if an angle is obtuse, then it measures 100. So that looks good so far. The inverse is if I do, I negate this. So I negate this, I negate this. So we say does not measure 100. If it does not measure 100, then it is not obtuse, right? So if an angle does not measure 100, then it is not obtuse. That looks good. That also, it does not say that in B. So we're going to cross B out. Also, we're going to cross D out. So that's not correct. Okay, so it looks like it's between A and C so far. The contrapositive is we do this, but then we switch it, right? So we're going to switch it. So if it is not obtuse, then it is not 100 degrees, right? Measure 100 degrees. So contrapositive, if an angle is not obtuse, then this does not measure 100. So it's between A and C, essentially, okay? So we're going to cross out B. We're going to cross out D. It looks like between A and C. However, we need to determine whether it's true or false. Okay, so let me erase this. So if an angle is obtuse, then it measures 100. Is that true? If obtuse, then it has to be 100. Well, that can't be true, because if an angle is obtuse, it doesn't necessarily mean that it has to measure 100. It could measure 120, right? So this cannot be true. So it has to be false. So therefore, I'm going to say that it is C. Okay. So again, do the condition, do the converse, inverse, and then see if it's true or not. All right, example 2. If two lines intersect, then the lines are coplanar. Identify the following statements as contrapositive, converse, or inverse. If two lines do not intersect, then the lines are not coplanar. Okay, so if the two lines intersect, then they're coplanar. This is like P, this is like Q. Converse is when you switch them, right? So you're going to do Q, and Q implies P. So switch them for the converse. So then if the lines are coplanar, then they intersect. If the lines are coplanar, then they intersect. This is the converse. The inverse is you negate them, right? So you negate them. So the opposite of that, opposite of that. So if two lines do not intersect, then they are not coplanar. Do not intersect, then they're not coplanar. This is the inverse. And then the contrapositive, you do both. You do the inverse, and then you also do the converse. So this is this guy, contrapositive. All right, that takes care of that benchmark. The next one is judging the validity and give counterexamples to disproved statements. All right. So statements 1 and 2 are true conditional statements. Statement 1, if a figure is a square, then it is a rectangle. Statement 2, if a figure is a rectangle, then it is a parallelogram. Which conclusion is valid? All right, so if figure A is a square, then figure A is a parallelogram. So is that valid? Okay, so let's go ahead and use it. Say figure, let's say, if a figure is a square, so let's say P, then it is a rectangle. And okay, now if a figure is a rectangle, so that's Q, right? It's the same statement, rectangle, rectangle, so they're both the same statement. We're going to call them both Q. If it's a rectangle, then it is a parallelogram. So that's a different statement. So we're going to call that R. So we got P, Q, and R. So we got 3 unique statements. This is saying if P implies, so P implies Q, and then statement 2 is Q implies R. Well, if P implies Q and Q implies R, that means that P must imply R. All right, and that is known as the law of syllogism. Okay, this is the law of syllogism. So so basically, if a figure is a square, then it is a rectangle. Well, if it's a rectangle, then it's a parallelogram. Well, then that means that if it's a square, it must be a parallelogram, right? By the law of syllogism. So answer A is true. Now, if I look at choice B, if figure A is not a square, then it is not a parallelogram. That's not necessarily true, right? Because if the figure happens to be a rectangle, which is not a square, then it is a parallelogram. So this actually would contradict statement 2, right? Where if it's a rectangle, then it would be a parallelogram. So that's a contradiction. So that can't be a true conditional statement always, right? If figure A is a parallelogram, then figure A is a square. Now this doesn't necessarily work the other way around, right? This is only one directional. So if it's a parallelogram, that doesn't mean that it's a square. It could be a rectangle, right? If figure A is a rectangle, then figure A is a square. Again, it doesn't work in reverse. So that's saying Q implies P, right? This is not two directional. It's only one directional. It's P implies Q, but that doesn't mean Q implies P. So the answer is A. All right. So in this case, if I look at example 2, determine whether the conclusion is valid based on the information, write valid or invalid, and explain. So if a figure is a square, then it has 4 right angles. Well, figure ABCD has 4 angles. So what can we conclude? Can we conclude that figure ABCD is a square? So is this valid or invalid? Well, this is actually invalid. Okay, and the reason is because if a figure is a square, so this is statement P, then it has 4 right angles. So this is saying P implies Q. If it's a square, then it has 4 right angles. This does not work in reverse, because if it has 4 right angles, that doesn't necessarily mean that it's a square, right? It could be a rectangle, it could be something else. So it doesn't work in reverse. So basically they're saying that it has 4 angles, right? So it's saying that it implies that Q is true, but if Q is true, that doesn't mean that you can go in reverse and say that P is true, that it's a square. So this is invalid, okay? Now, if they said that figure ABCD is a square, right? Then by the law of detachment, we could say that it has 4 right angles. So if ABCD has or is a square, I'm just going to do this shape for is a square, then it has 4 right angles. That is the law of detachment, but you cannot reverse it to get the law of detachment, right? So this is invalid. All right, so is the conclusion valid based on the information given? Explain your reasoning. If it is Wednesday or Friday, then Sarah goes to physical therapy. Sarah went to physical therapy today. Conclusion, today is Wednesday or Friday. Okay, so if it is Wednesday or Friday, so this is statement P, right? Then Sarah goes to physical therapy. So P implies Q there, right? Today is Wednesday or Friday. So they're saying that oh no, it says Sarah went to physical therapy today. So basically they're saying that this is true, that Q is true. Can we go backwards to conclude that it's Wednesday or Friday? And the answer is no. This doesn't work backwards, right? It does not work the other way around. It does not work this way. You can't go from right to left. You gotta go from left to right. So if we know it's Wednesday or Friday, then we know that Sarah is at physical therapy. But if Sarah went to physical therapy and that's all the information we know, that does not mean that it's going to be Wednesday or Friday. She could have attended an extra day, right? It could have been she probably changed an appointment and maybe she went on Thursday instead of Friday, right? Or Thursday instead of Wednesday. So we can't necessarily conclude that. So it's invalid. The hypothesis, we don't know whether the P is satisfied, right? The hypothesis, which is Wednesday or Friday. So we cannot conclude that that's the case. All right, so this is invalid. Hopefully that makes sense. All right, guys, that's going to do it for the end of the video. I hope you learned a few things or were able to kind of review. And as usual, I'll see you in the next one.